Hello. I'm so glad you found your way here, because tonight we aren't just stargazing. We're exploring something closer, something invisible, something that holds our entire galaxy together, yet can never be seen directly. Tonight, we're exploring Sagittarius A star, the supermassive black hole at the heart of the Milky Way, 27,000 light-years away, and yet this is our black hole, the monster in our backyard, 4 million times the sun's mass, compressed into silence and darkness, anchoring everything we know. Welcome to the Sleepy Astronomer. If this is your first journey with me, welcome aboard. And if you've travelled with me before through the quiet wonders of space, it's wonderful to have you back among the stars. If this exploration helps you unwind or fills you with quiet wonder as you drift towards sleep, feel free to give the video a like. And if you'd like to help others discover these peaceful cosmic journeys, a subscription truly helps this little corner of the universe grow. So, settle in, find your most comfortable position, and let your thoughts drift as we begin our gentle journey to silence at the center of everything with facts that reveal our galaxy's hidden architecture, numbers that connect us to the heart of home, and truths about the invisible anchor that holds 400 billion stars in their orbits. From invisible radio whisper to photographed shadow, from mathematical prediction to measured reality, from the boundary of the knowable to the center we'll never fully understand, where silence holds everything together and reminds us that even darkness can be home. 27,000 light-years. That's the distance to the center of everything we know, not the center of the universe. That doesn't exist, but the center of home, the Milky Way's heart, the point around which 400 billion stars orbit, including ours. 27,000 light-years means the light we detect today left when humans were still painting on cave walls, long before recorded history began. The signal is old, ancient even, but what it reveals is timeless. At that distance sits Sagittarius A star, containing 4 million times the sun's mass, compressed into a region smaller than Mercury's orbit. Close enough to study in detail, far enough that its gravity doesn't threaten us, the perfect distance for understanding without danger, the monster in our backyard, close enough to photograph yet far enough to feel safe. We orbit it, distantly, through the sun's own orbit around the galactic center. Our entire solar system makes this journey once every 230 million years. One cosmic year, one galactic orbit, and at the center of that vast circle sits Sagittarius A star, holding us in its distant gravitational embrace. It lies in the direction of the constellation Sagittarius, where the Milky Way looks brightest from Earth. If you could see the full sky without light pollution, without the interference of city glow, you'd notice something remarkable. The band of the Milky Way grows thicker, brighter, more concentrated in one particular region. That's where we're looking when we point our telescopes toward the galactic center, toward Sagittarius, toward home's heart, toward the place where stars crowd together more densely than anywhere else in our galaxy, where light from billions of distant suns merges into that soft milky glow that gave our galaxy its name. The star symbol is pronounced star, but it marks something far darker than any star. It's a designation, a label chosen by astronomers to distinguish this particular radio source from others nearby. Sagittarius A star, not because it shines like a star, but because the naming convention required something to differentiate it from the broader Sagittarius A region. The irony isn't lost on anyone. Calling a black hole star when it's the absence of starlight the ending of light itself. But names are just sounds we make to point at mysteries, and this mystery needed a name. Something to call it, something to write in papers and speak in conferences. So Sagittarius A star it became, the star that isn't a star, the light that is darkness. Early radio astronomers in 1951 first detected unusual radio emissions from the galactic center. They weren't looking for a black hole. They didn't know what a black hole was yet. The term hadn't even been coined. They were simply mapping the sky in radio wavelengths, documenting what the universe whispered in frequencies our eyes couldn't see. And there, in the direction of Sagittarius, they found something strange. A source of radio waves, persistent and bright, coming from the densest part of the Milky Way's band. Something was there, hidden behind dust and distance, sending out a signal. A whisper through the cosmic static, calling attention to itself through sheer persistence. These emissions came from work that began even earlier. Karl Jansky's pioneering discoveries in 1932. Jansky wasn't an astronomer by training. He was an engineer for Bell Labs, tasked with investigating static that interfered with radio communications. He built an antenna and began listening to the sky, and discovered something unexpected. Most of the static came from thunderstorms as expected, but one source of interference kept appearing, moving across the sky with the stars rather than with the sun. It peaked once every 23 hours and 56 minutes, a sidereal day, the time it takes for the Earth to rotate once relative to the distant stars rather than relative to the sun. Jansky realized he was detecting radio waves from space itself, not from the sun, not from planets, but from the stars, from the galaxy, from the structure of space around us, and the strongest source came from the direction of Sagittarius, from the galactic center. He'd found the radio voice of the Milky Way's heart without knowing what was speaking, without understanding what could generate such persistent radio emission from so far away. For decades after Jansky's discovery, that voice remained mysterious. Astronomers knew something massive and strange occupied the galactic center, but they couldn't see it in visible light. The dust was too thick, the distance too great, the obscuration too complete. They could only listen to its radio whisper and wonder what lay hidden there. What kind of object could produce such signals? A whisper that would eventually lead us to understand the silence at the center. The whisper that revealed a black hole, waiting in darkness, holding everything together through gravity alone. 4 million solar masses compressed into stillness, anchoring our galaxy while remaining invisible to every wavelength except those patient enough to reveal its presence. The heart of home, found through listening, through patience, through following a radio signal across 27,000 light-years of space and decades of human curiosity, through refusing to accept that invisibility meant absence. We couldn't see it yet, but we knew it was there, speaking softly in frequencies that pierced the dust, calling us to understand the invisible architecture of everything we call home, reminding us that even darkness can be home when it's the darkness that holds everything together. In 1974, Bruce Ballack and Robert Brown confirmed what others had suspected for decades. The compact radio source at the galactic center wasn't a cluster of objects. It wasn't multiple sources overlapping. It was singular, compact, bright, and it had a name now: Sagittarius A star. Confirmation came through careful measurement, patient observation, the kind of astronomy that requires staring at the same patch of sky for months and years, watching for changes, measuring positions, refining coordinates, making sure the signal wasn't a mistake, wasn't interference, wasn't wishful thinking. It was real. It was there. And it was remarkably small for something so bright in radio waves. The region spans just 44 million kilometers. That's roughly the distance from the Sun to Mercury's orbit. Imagine Mercury's entire path around our star, that elliptical loop the tiny planet traces, and you've approximated the size of Sagittarius A star's event horizon. Now imagine compressing 4 million suns into that space. 4 million stars like ours, all their matter, all their mass, squeezed into a region smaller than Mercury's orbit. The density becomes incomprehensible. The gravity becomes absolute. Nothing else could be that massive and that compact. A cluster of stars wouldn't work. They'd be torn apart by mutual gravitational interactions scattered over time. A dense gas cloud wouldn't work either. Radiation pressure would blow it apart. A neutron star? They can't exceed about 3 solar masses before collapsing into black holes themselves. Only one object fits the evidence. Only one explanation makes sense. A supermassive black hole sitting silent at the center, bending space-time around it like a weight on a rubber sheet, holding the galaxy together through pure gravitational architecture. That density left only one explanation, but explaining something doesn't make it less strange. 4 million times the Sun's mass, compressed into a point where space-time curves back on itself, where the normal rules of physics break down, where even light cannot escape. And this isn't some distant mystery. This is home. This is the center of our galaxy, the thing around which we orbit, along with 400 billion other stars, each on their own path through the Milky Way's structure. It sits amid the nuclear stellar cluster, one of the densest concentrations of stars anywhere in the galaxy. Think of your local neighborhood in space. Within a few light years of Earth, there might be a handful of stars, maybe a dozen if we're generous. The space around us is mostly empty, vast distances between stellar neighbors. Now travel to the galactic center. Within that same volume, you'd find not dozens but thousands of stars. They crowd together, their gravity tangling, their light overlapping. It's a stellar city compared to our cosmic countryside. In this region, a single cubic light-year contains 1 million times more stars than our local neighborhood. A cubic light-year is already almost impossibly large to imagine. A cube where each edge is the distance light travels in 1 year, about 9.5 trillion kilometers per edge, and in that enormous volume near the galactic center, stars pack so densely that collisions become possible, though still rare. Close encounters happen regularly. Orbits shift and change over time. It's crowded there, in a way that's hard to comprehend from our quiet corner of the galaxy. We're out in the suburbs where space is spacious, where stars have room to breathe. But the galactic center, that's downtown. That's where everything concentrates, where the density peaks, where the black hole's gravity holds millions of stars in complex interwoven orbits. And at the very center of this stellar metropolis sits Sagittarius A star. Not moving, not orbiting, just sitting there, as stars whirl around it at tremendous speeds, as gas clouds drift past, as the entire nuclear cluster performs its slow gravitational dance. The monster in our backyard turned out to be exactly where the galaxy's heart should be, at the densest point, the gravitational anchor, the place where everything converges, not by accident, not by chance, but because that's how galaxies work. The supermassive black hole doesn't just sit at the center. It helped shape the galaxy itself, its gravity influencing star formation and orbital dynamics across billions of years. We found it through radio whispers. We confirmed it through careful measurement, and slowly, over decades of observation and theoretical work, we came to understand what it meant. That home has a black hole at its heart, that darkness can be an anchor, that the center of everything we know is a region where light goes to die, yet somehow that makes perfect sense. 4 million solar masses, 44 million kilometers across, hidden among millions of stars, invisible light, yet there, unmistakably there, holding everything together through the simple, patient work of gravity. The confirmation brought clarity, but it also brought deeper questions. How did it form? How did it grow so massive? What happens to the stars that orbit so close? And could we ever, somehow, actually see this invisible giant? Those questions would take decades more to answer, but in 1974, the first step was complete. We knew what sat at the center. We knew its approximate mass and size. We knew it was real. The monster in our backyard had a name, a location, and a description. Now we just had to figure out how to see it. And for that, we'd need to learn how to see the invisible. We can't see Sagittarius A star invisible light. Not because it's too far away, though 27,000 light-years is certainly far. Not because it's too small, though fitting 4 million suns into Mercury's orbit does make for a compact object. We can't see it because of something much simpler, much more mundane. Dust. Between us and the galactic center lies 27,000 light-years of space, and throughout that space, scattered like fog through a valley, hangs dust. Not household dust, though the comparison isn't entirely wrong. Interstellar dust. Tiny particles of carbon, silicon, complex organic molecules, the debris of stellar death and birth scattered through the galaxy over billions of years. This dust doesn't just dim visible light, it obliterates it. It absorbs those wavelengths almost completely, scatters them in every direction, reduces them to nothing. Look toward Sagittarius with an optical telescope, and you see almost nothing where the galactic center should be. Just darkness and a few foreground stars. The dust absorbs and scatters visible light, making the galactic center about 1 billion times dimmer optically than it would be otherwise. 1 billion. Not 1 million. 1 billion. It's like trying to see a candle through a mile of thick fog. The light is there, somewhere, but it never reaches your eyes in any useful form. For centuries this presented a problem. The galaxy's heart remained invisible, not because nothing was there, but because we were looking with the wrong kind of light. The universe was hiding its deepest secret behind a curtain of ancient dust, and we didn't yet know how to peek around it. But dust has preferences. It blocks some wavelengths and allows others to pass through. Visible light? Blocked. Infrared? Much better. Radio waves? They pass through dust like it isn't even there, completely unbothered by particles too small to interfere with their long wavelengths. Infrared and radio telescopes pierce that dust curtain, revealing the hidden heart underneath. They see through the fog. They look past the obscuration. They find what visible light cannot reach. And what they found was Sagittarius A star, glowing softly in radio frequencies, announcing its presence despite the billion-fold dimming invisible light. Sagittarius A star emits radio waves, X-rays, and occasional flares, but no visible glow, no light our eyes could see, even if we could get close enough, even if we could clear away all that dust. Because the black hole itself produces no light. Its light, if you can call it that, is trapped below the event horizon, caught in the gravitational well, unable to escape. The point of no return, the boundary where space-time curves so severely that all paths lead inward, where escape velocity exceeds the speed of light, where physics itself seems to say, this far and no farther. Below that boundary, information cannot escape. Light cannot escape. Nothing can escape. because nothing can move faster than light, and even light isn't fast enough. So the black hole sits in silence and darkness, invisible by nature, even before you add 27,000 light-years of dust. It doesn't glow, it doesn't shine, it doesn't announce itself in visible wavelengths. It simply exists, a gravitational well so deep that light falls in and never climbs back out. But the region around the event horizon, that's a different story. Gas and dust spiral inward, heating up through friction and compression, glowing in X-rays and radio waves before crossing that final boundary. The accretion disk announces what the black hole cannot. The material falling in tells us what's there, even though the thing itself remains hidden. It's an interesting cosmic irony. The black hole is invisible because its gravity is so strong that light cannot escape, but that same gravity pulls material inward, and that material glows brightly enough to see from 27,000 light-years away, even through a billion-fold reduction in visible light. The monster reveals itself through what it eats, through the last gasps of matter before disappearing forever, through the radiation emitted by doomed gas clouds in their final moments before crossing the event horizon. We found it in radio wavelengths, we studied it in infrared, we watched it flare in X-rays, and slowly, over decades, we built an understanding of something we could never see directly. Something hidden by dust, hidden by distance, hidden by its own nature as a region where light goes to die. Hidden in plain sight, you might say, if plain sight could see through a billion-fold dimming and look in wavelengths our eyes can't perceive. The galactic center has always been there, in that direction, at that distance. We just needed to learn how to look properly, how to see with radio ears instead of optical eyes, how to understand that invisibility doesn't mean absence. The dust taught us something important, that the universe doesn't always reveal itself in the wavelengths we prefer, that some mysteries require us to look differently, to expand our perception, to stop insisting on visible light when radio waves will do just fine. And beneath that dust curtain, beneath 27,000 light-years of ancient stellar debris, the heart of our galaxy waited patiently to be found, silent, dark, invisible to our eyes, but there, unmistakably there, holding everything together while remaining forever hidden from direct view. Even darkness can be home, especially when it's the kind of darkness that anchors galaxies. The black hole's diameter is about 24 million kilometers, just 17 times wider than the Sun. That sounds almost modest, doesn't it? Only 17 suns lined up in a row to span the event horizon. The Sun itself is already enormous, over 1 million kilometers across, large enough to fit more than 1 million Earths inside. And Sagittarius A star's event horizon is only 17 times that. But here's where the numbers start to feel strange. Despite that relatively modest size, the black hole weighs more than 4.3 million suns combined. 4,300,000 solar masses compressed into a region you could fit between the Sun and Mercury with a room to spare. The density becomes incomprehensible. All that mass, all that matter, squeezed into such a small volume that space-time itself can't handle it anymore. It curves, it bends, it warps into something that barely resembles the flat geometry we're used to. And at the very center, according to the mathematics, sits a singularity, a point of infinite density where the equations break down and physics stops making sense. Though whether the singularity actually exists is still debated. Some theories suggest quantum effects prevent true infinite density, but we can't see inside to check, so the singularity remains theoretical, hidden behind the event horizon where observation cannot reach. The gravitational pull is so intense that time itself slows near the event horizon. Not metaphorically, not approximately, actually slows, measured against clocks farther away. Einstein taught us this. Time is not absolute. It flows at different rates depending on gravity and motion. Near strong gravity, time slows down. At the event horizon of Sagittarius A star, this effect becomes extreme. A clock there would tick slower than a clock on Earth, not slightly slower, dramatically slower. Someone orbiting just outside the event horizon would experience time passing normally for themselves. Their heartbeat would feel normal, their thoughts would progress at their usual pace, their watch would tick forward second by second. But watching them from a safe distance, you'd see them move in slow motion. Their clocks would appear to run slowly. Their aging would appear to slow. This isn't an illusion or trick of perception. Time genuinely flows at different rates in different gravitational fields. Near the event horizon, space-time is so warped, so curved by the black hole's mass, that time itself bends under the strain. The closer you get, the slower time flows, until at the horizon itself, from an outside perspective, time appears to stop entirely. Objects falling toward the event horizon seem to freeze, to hang there forever, never quite crossing the boundary. Though from their own perspective they fall through just fine, experiencing nothing special at the moment of crossing except the knowledge that there's no turning back. Gas and dust spiral inward at nearly the speed of light before crossing the boundary. They've been falling for a long time by then, accelerating gradually, gaining speed as they drop deeper into the gravitational well. By the time they approach the event horizon, they're moving at tremendous velocities, 20, 30, 50% of light speed, sometimes more. At those speeds, strange things happen. Distances compress. Time dilates. The normal rules of everyday physics give way to relativistic effects, where mass increases with velocity, where nothing with mass can quite reach light speed no matter how much it accelerates. The gas spirals because it has angular momentum. It can't fall straight in. It has to circle first, gradually losing energy through friction and radiation, slowly spiraling inward like water circling a drain. Except this drain leads to a place where space and time exchange roles, where the future points inward rather than forward, where escape becomes mathematically impossible. When matter falls in, friction heats it to tens of millions of degrees before disappearing forever. This friction comes from particles rubbing against each other, from magnetic fields tangling and snapping, from the sheer violence of material trying to occupy the same orbital space. The gas doesn't fall quietly. It flares in X-rays and radio waves as it fades. Tens of millions of degrees, hot enough to glow in high-energy wavelengths invisible to our eyes, but bright to instruments designed to detect them. The material gets one last chance to shine, to announce its existence, to say, "I was here," before crossing the event horizon and vanishing from the observable universe forever. And then it's gone. Not destroyed, technically. Mass and energy are conserved, added to the black hole's total, but gone from our perspective, removed from the universe we can interact with, fallen beyond the boundary where information can return. The event horizon isn't a physical surface. There's nothing there to touch, nothing solid. It's just a mathematical boundary, a point of no return defined by where escape velocity equals light speed. Cross it, and you're committed. Turn around, and you'll find that all paths lead inward now. The geometry of space-time itself conspires to pull you toward the singularity, regardless of which direction you think you're moving. It's the ultimate one-way door, the final boundary, the edge of the knowable universe in a sense. Everything beyond remains forever hidden, forever inaccessible, forever mysterious. And at the center of our galaxy, this boundary sits quiet and patient, occasionally swallowing gas and dust, gradually growing more massive, holding 400 billion stars in their orbits through gravity alone. Not trying to be dramatic about it, not announcing itself, just existing, doing what black holes do, being the gravitational anchor at the heart of home. The physics is strange, the mathematics is elegant, the reality is invisible, but it's there, unmistakably there, bending time and space and light around it, reminding us that even darkness can be home when the darkness holds everything together. Because of its proximity, Sagittarius A star is the best natural laboratory for testing general relativity. 27,000 light-years might not sound particularly close. It's not somewhere you'd pop over to for a weekend visit. But in cosmic terms, in the scale of galaxies and universe-spanning distances, it's practically in our backyard. More importantly, we can resolve individual stars orbiting it. We can track their motions across the sky, watch them move from year to year, plot their paths with extraordinary precision. Most supermassive black holes live in galaxies so distant that we see only their collective glow. We can't pick out individual stars. We can't watch their orbits. We can only observe the overall behavior of the galactic center. But Sagittarius I star? We can see its neighborhood in detail. We can watch stars orbit it the way astronomers in other galaxies might dream of doing but cannot. It's close enough, and our telescopes are good enough, that we can do real observational astronomy on individual stellar orbits around a supermassive black hole. This makes it perfect for testing Einstein's predictions. General relativity makes very specific claims about how gravity works, how space-time curves, how objects move through that curved geometry. And near a supermassive black hole, those effects become measurable, become detectable, become something we can actually observe rather than just calculate. Astronomers can track individual stars orbiting it to test Einstein's predictions. Dozens of stars, actually, each with its own orbit, its own period, its own closest approach distance. They've been watching these stars for decades now, building up a catalogue of positions and velocities, watching the gravitational ballet play out in real time. Well, delayed time. The light we see today left 27,000 years ago. But you get the idea. The star, S2, completes one full orbit every 16 years, fast for such a massive orbit. Jupiter takes 12 years to orbit the Sun, travelling a much smaller distance. S2's orbit is enormous by comparison, yet it completes the circuit in just 16 years because it's orbiting something 4 million times more massive than the Sun. 16 years. That's fast enough that astronomers have watched it complete multiple orbits now. They caught it in 1992. They've tracked it through 1995, 2002, 2018, and most recently in 2034. Well, no, wait. Let me check my calendar. We're still waiting on that one. But they've tracked it through more than one complete orbit, which means they know its path intimately. They've measured it thoroughly. They understand where it goes and how fast it moves. S2 became famous not by choice but by proximity. Among dozens of stars orbiting the galactic center, S2 has an orbit that brings it extraordinarily close to Sagittarius A star. Every 16 years, it screams past the black hole at its closest approach, then drifts back out to its farthest point before returning. During its closest approach, S2 travels at over 25 million kilometers per hour. That's roughly 2.5% of the speed of light, 25 million kilometers per hour, fast enough to cross the diameter of Earth in about half a second. Fast enough that if you could somehow watch it from nearby, it would be a blur, a streak of light moving so quickly that your brain couldn't quite process it. At that speed and proximity, relativistic effects become measurable, not theoretical, not hypothetical, actually measurable with real telescopes and real instruments. The effects Einstein predicted over a century ago become observable phenomena that we can detect from 27,000 light-years away. S2's light shifts to redder wavelengths during closest approach. This is gravitational redshift. Light climbing out of a deep gravitational well loses energy, which means its wavelength stretches, which means it appears redder than it should. The effect is tiny, but it's there, detectable, measurable, precisely what Einstein's equations predict. The star's orbit also precesses, rotating slightly with each pass, like a spinning top that wobbles as it spins. Newtonian gravity predicts the orbit should be a perfect closed ellipse, returning to exactly the same points each time. But general relativity says no. The orbit should twist slightly, should rotate gradually over time. And that's exactly what observers see. At these speeds, through this gravitational field, the differences between Newton and Einstein become visible. Newton's mathematics works beautifully for most situations, launching satellites, landing on the moon, navigating the solar system. But near Sagittarius A star, Newton's predictions diverge from what actually happens. His equations are close, but not quite right. Einstein's equations, meanwhile, predict S2's motion to extraordinary accuracy. They account for the gravitational redshift. They predict the orbital precession. They explain what Newton cannot. And every time S2 completes another orbit, every time astronomers gather more data, Einstein's century-old mathematics continues to match reality with remarkable precision. This is what makes Sagittarius A star such a valuable laboratory. It's not that we doubt Einstein. His theory has been tested in countless ways over the past 100 years. But there's something satisfying about watching a star orbit a black hole at 2.5% of light speed and seeing general relativity proven right yet again. Each observation refines the map. Each measurement constrains the black hole's properties more tightly. Each orbit lets us test physics in conditions we can create nowhere else: extreme gravity, high velocities, curved space-time. The kind of environment where the universe reveals its deeper structure, where the mathematics of reality becomes visible in stellar motion. S2 became the standard for testing relativity in extreme gravity. Not because it's special, not because it's unusual, simply because its orbit is fast and it gets close, and we can measure it. The perfect test subject, orbiting patiently while astronomers watch, gathering the data needed to confirm what Einstein suspected all along. That gravity isn't a force pulling objects together, that it's the shape of space-time itself, curved by mass. Guiding objects along paths we call orbits, and S2, speeding around Sagittarius A star every 16 years, proves it with every closest approach. S2's light shifts to redder wavelengths during closest approach, proving gravitational redshift, not just suggesting it, not hinting at it, proving it. The effect is exactly what Einstein predicted. Light climbing out of a gravitational well loses energy, stretches to longer wavelengths, appears redder than it should based on the star's actual temperature and composition. Astronomers measure this by comparing S2's spectrum at different points in its orbit. When it's far from the black hole, its light looks normal for a star of its type, but during closest approach, when it's deep in Sagittarius A star's gravitational field, the wavelengths shift. The amount of shift matches Einstein's equations to remarkable precision. These measurements confirmed Einstein's theory to within 0.3% accuracy. Extraordinary precision for observing something 27,000 light-years away, moving at 2.5% of light speed through one of the most extreme gravitational environments we can study. 0.3%. That's the margin within which Einstein's predictions match the observations. After accounting for all the measurements, all the tracking data, all the orbital mechanics, general relativity predicts what S2 should do. And S2 does exactly that, to within 0.3% accuracy. This is remarkable. We're testing a theory published in 1915, using observations of a star orbiting a black hole 27,000 light-years away, moving at speeds that make Newton's equations break down. The fact that century-old mathematics predicts this motion to such precision tells us something profound about reality. That Einstein understood something fundamental, that his mathematical description of gravity as curved space-time isn't approximation or metaphor, it's accurate. Deep truth about how the universe works, confirmed by watching stars dance around darkness. The orbits form elegant ellipses, like a dance around an invisible partner. Perfect mathematical curves trace through space over years and decades. Each star follows its own ellipse, its own path, determined by its velocity and the black hole's mass and the geometry of space-time itself. From our perspective, watching from 27,000 light-years away, these orbits appear as graceful loops projected onto the sky. The stars drift across the galactic center, marking their paths like dancers on a dark stage. Some move quickly, some move slowly, but all follow ellipses, the natural shape of orbital motion. This stellar ballet revealed the black hole's mass long before we photographed its shadow. By measuring the orbits, astronomers could calculate exactly how massive the central object must be. The math is straightforward. Kepler's laws, refined by Einstein, applied to stellar motion. The orbital periods and distances tell you the mass of whatever they're orbiting. 4.3 million solar masses. That's what the orbits revealed. Not from seeing the black hole, not from detecting it directly, but from watching how stars move around it, the way you might deduce the presence of a person spinning a ball on a string by watching the ball's circular motion, even if the person remained invisible. The orbits don't lie. They can't. They're governed by gravity and geometry, by mathematics that doesn't care about obscuration or invisibility. The stars trace their paths according to the mass they orbit, and those paths tell us everything we need to know about what sits at the center. Every orbit lets scientists refine the map of space-time near the event horizon. Each time S2 completes another 16-year circuit, we gather more data. Each time another S-star passes through its closest approach, we get another data point. The picture becomes clearer. The measurements become more precise. The uncertainties shrink. It's patient work, decades of observation, nights and nights of telescope time, tracking stars that move slowly across the sky from our perspective, waiting for S2 to complete its orbit, watching S4714 and S62 and dozens of others trace their paths through the gravitational field. But that patience pays off. With each orbit, we understand the black hole better. We constrain its mass more tightly. We measure its position more precisely. We test general relativity in conditions more extreme than anywhere else we can study. The stellar ballet continues, has continued for millions of years before we started watching, will continue for millions more after we're gone. The stars don't know they're teaching us physics. They're just following space-time's curvature, taking the straightest possible paths through geometry that's anything but flat. And we get to watch, to measure, to learn, to see Einstein's mathematics proven right over and over again, with every closest approach, with every completed orbit, with every measurement that matches prediction to within fractions of a percent. No other environment in the universe gives such clear proof of gravity's curvature. No other place lets us watch individual stars orbit a supermassive black hole, tracking their motion year by year, testing relativity in real time. Sagittarius A star isn't just the heart of our galaxy. It's our laboratory, our classroom, our window into physics at its most extreme. The monster in our backyard turned out to be a teacher, patient, silent, invisible to our eyes, but perfectly visible in the motion of stars that orbit it, holding still at the center while everything else dances around it, following paths carved into space-time by 4 million solar masses compressed into darkness. Einstein would have loved it. The elegance of the orbits, the precision of the measurements, the way reality matches mathematics with such remarkable accuracy. His theory, tested to breaking point, and it doesn't break. It holds, it predicts, it explains. The stellar ballet continues, and we watch, learning what stars can teach us about the fabric of space and time. Dozens of S-stars orbit within a few light days of Sagittarius A star. Not light years, light days. The distance light travels in a single day, about 26 billion kilometers. That's roughly the distance from the Sun to the orbit of Pluto, maybe a bit farther depending on where Pluto happens to be in its elliptical path. Within that relatively tiny volume measured against galactic scales, dozens of stars orbit the black hole, each following its own ellipse, each moving at its own speed, each taking its own time to complete a circuit. They've been named systematically S1, S2, S4, S5, continuing through the catalogue as astronomers discover and track more. S2 is just the most famous, the one that gets the spotlight, the one whose orbit has been measured most thoroughly, whose properties are best understood, whose motion has tested Einstein's predictions most precisely. But it's not alone. It's not even the most extreme example of what happens near the galactic centre. S2 is just the most famous. Others like S62 and S4714 move even faster. These stars have tighter orbits, closer approaches, higher velocities. They scream around Sagittarius I star at speeds that make S2 look almost leisurely by comparison. Almost. S4714 holds the record, the fastest known star in our galaxy, perhaps in any galaxy we've measured. It reaches 8% of light speed during its closest approach to the black hole. 8%. That's 24,000 kilometers per second. Fast enough to cross the diameter of Earth in about half a second. Fast enough to travel from Earth to the Moon in 16 seconds. At these speeds, the stars experience measurable time dilation, not just theoretical time dilation that requires extremely sensitive instruments to detect. Measurable time dilation, the kind you could observe with a good clock if you could somehow get close enough to watch. A clock on S4714 would tick slower than a clock on Earth. Not by much, we're talking about 8% of light speed, not 90%. But enough to measure, enough to detect, enough that time genuinely flows at different rates for the star versus for us, watching from our distant perspective. The star itself doesn't notice. Time passes normally from its own reference frame. Its stellar processes continue at their usual pace. If it somehow supported life, which it definitely doesn't, being a massive hot star in an extremely hostile environment, that life would experience time flowing normally. Their seconds would feel like seconds. Their years would feel like years. But watching from Earth, from our reference frame, we'd see their clocks run slow. Their processes would appear slightly slowed down. The relativistic effects would be subtle but real, encoded in the light we receive, in the measurements we make, in the way physics works near extreme velocities. The star's orbits twist slightly each time, relativistic precession predicted by Einstein. Not just S2, all of them. Every S-star that orbits close enough, fast enough, through strong enough gravitational fields shows this effect. Their ellipses don't quite close. They rotate gradually, like spinning tops that wobble as they spin. Newton's gravity predicts closed ellipses, perfect repeating paths that return to exactly the same points each orbit. But Einstein's gravity says the ellipses should precess, should rotate, should shift slightly with each pass. And that's exactly what observers see when they track these orbits over years and decades. The amount of precession depends on how close the star gets, how fast it moves, how strong the gravitational field is at closest approach. S4, 714, moving faster and getting closer than most, shows more precession. Its orbit twists more dramatically than S2's. The effect is larger, easier to measure, more obvious in the data. Watching S4714 is like watching Einstein's equations come alive. Here's a massive object, a star, moving so fast that the fabric of space-time struggles to keep up. And it does this not occasionally but regularly, every orbit bringing it screaming around the black hole at speeds that make special relativity mandatory, not optional. At 8% of light speed, you can't ignore relativistic effects anymore. They're not small corrections you add to Newtonian calculations. They're fundamental to understanding what's happening. The star's momentum becomes relativistic. Its energy includes significant mass-energy contributions. Time dilation becomes noticeable. Length contraction occurs, though from the star's perspective it's the universe that's contracted, not itself. No other environment in the universe gives such clear proof of gravity's curvature, of velocity's effects on time, of spacetime's fundamental role in motion. We can study particle accelerators on Earth, sure. We can watch particles move at 99% of light speed, but watching an entire star, something massive and bright and trackable, move at 8% of light speed through the strongest gravitational field we can observe, that's unique to Sagittarius A star. The monster in our backyard provides the perfect laboratory, close enough to observe in detail, extreme enough to make relativistic effects obvious, patient enough to let us watch orbit after orbit, gathering data, refining measurements, testing predictions. And S4714 doesn't mind being the example, doesn't know it's the fastest star in the galaxy, doesn't care that astronomers track its every move, calculate its every property, use it to test century-old physics. It just orbits, following space-time's curvature, taking the straightest path through geometry that's anything but straight. Fast, extreme, measurable, and teaching us about the universe with every closest approach. No other environment in the universe gives such clear proof of gravity's curvature. Not even close. We've tested general relativity in many ways over the past century. The bending of starlight during solar eclipses, the precession of Mercury's orbit, gravitational waves from merging black holes, time dilation in GPS satellites orbiting Earth. All of these tests confirm Einstein's predictions. All of them show that gravity is curved space-time, not a force pulling objects together. But none of them match the clarity, the precision, the sheer observability of watching stars orbit Sagittarius A star. Here we can see individual objects moving through extreme gravity at extreme speeds, following paths we can measure year after year, orbit after orbit. The evidence doesn't require sophisticated instruments detecting ripples in space-time or subtle shifts in atomic clocks. You can literally watch stars move across images, plot their positions, calculate their orbits, and see Einstein's mathematics proven right. Some stars likely began farther out and migrated inward through gravitational interactions. Not all of them formed where they orbit now. In the crowded environment near the galactic center, stars interact. They pass close to each other. Their gravitational fields interfere. Sometimes these interactions add energy to a star's orbit, flinging it outward. Sometimes they remove energy, causing the star to spiral inward. Over millions of years, this process called dynamical friction shuffles stars around the galactic center. Some drift outward and escape the nuclear cluster entirely. Others sink inward, finding tighter orbits closer to the black hole. The S-stars we observe today may have started their lives much farther out, gradually migrating inward through countless gravitational encounters. It's a slow process, very slow. Stars don't just suddenly jump to new orbits, but given enough time, given millions of years of interactions, the distribution of stars near the galactic center changes. Some stars end up on the extreme orbits we observe today, not because that's where they formed, but because gravitational interactions moved them there. Others may have formed in place from gas disks circling the black hole billions of years ago. This seems strange at first. How could stars form so close to a supermassive black hole? Wouldn't the tidal forces tear apart any gas cloud trying to collapse? But gas disks are different from individual clouds. A disk is already in orbit, already rotating, already stabilized by angular momentum. And within a stable disk, local regions can collapse to form stars, the same way stars form in the disk of any galaxy. The environment is more extreme, certainly. The tidal forces are stronger, but star formation remains possible under the right conditions. So some S-stars may be natives, born in the neighborhood they still inhabit. Others may be immigrants, drifted inward from farther out. We're still working out which is which, still piecing together the history of how these stellar orbits came to be. Their survival shows that even near a supermassive black hole, stars can thrive. You might think nothing could survive so close, that the tidal forces would rip stars apart, that the radiation environment would be lethal, that the violence of the galactic center would destroy everything. But supermassive black holes have gentler tidal forces at their event horizons than stellar mass ones. Size matters. A black hole containing 4 million solar masses has an event horizon large enough that the tidal gradient, the difference in gravitational pull between one side of an object and the other, is actually quite mild at the horizon itself. The S-stars orbit within light days of the event horizon, and they're fine. Not being torn apart, not being bombarded with deadly radiation, not being disrupted by the black hole's presence. They're simply orbiting, as they have for millions of years, perhaps longer. Their survival teaches us something important. The region near a supermassive black hole isn't necessarily a death zone. It can be a stable, functioning stellar ecosystem, complete with complex orbital dynamics and long-term stability. Stars can live full lives there. They can orbit safely for billions of years if their orbits remain stable. Could there be planets around these stars? Technically possible, though the formation of planets so close to the galactic center seems unlikely. The environment is turbulent, the gravitational interactions complex, the radiation intense. But physics doesn't forbid it, and the universe has surprised us before. Each orbit is a chapter in a story millions of years in the making. Every time S2 completes its 16-year circuit, that's one chapter. Every time S4714 screams past at 8% of light speed, that's another chapter. The story began long before humans existed. It will continue long after we're gone. We get to observe a tiny slice of it, a few decades of watching, a handful of orbits measured. In cosmic terms, we've barely started reading this story. But what we've read so far teaches us about gravity, about black holes, about the dynamics of extreme environments. The stars don't know they're teaching us, don't know we're watching. They just orbit, following space-time's curvature, living their stellar lives in the most extreme neighborhood in our galaxy. And we watch, patient and curious, learning what the universe reveals through their motion. Decades of patient watching, decades of data collection, decades of refining measurements and testing predictions. Astronomy at its most patient, most careful, most rewarding. The stellar ballet continues, and we're fortunate enough to have front row seats, even if those seats are 27,000 light-years away. In 2017, the Event Horizon Telescope Network began imaging Sagittarius A star. Not a single telescope, a network. Multiple radio dishes scattered across the planet, working together as one enormous virtual telescope. The kind of project that requires international cooperation, careful coordination, and a willingness to point extremely expensive instruments at the same tiny patch of sky for nights on end. The collaboration had been building toward this for years, planning, coordinating, adding new telescopes to the network, refining techniques, testing equipment, making sure everything would work when the time came to actually observe Sagittarius A star. It linked 8 radio telescopes from Hawaii to Chile to Antarctica into one virtual telescope, 8 separate facilities, each with its own team, its own equipment, its own challenges. The submillimeter array in Hawaii, the Atacama Large Millimeter Array in Chile, the South Pole Telescope in Antarctica, and 5 others spread across the globe. Each telescope observed independently, recording the radio waves arriving from Sagittarius A star. But the trick, the ingenious bit of engineering that makes this whole thing work, is that they recorded those signals with extremely precise timing. Atomic clocks at each site kept time to within nanoseconds. This precision let astronomers later combine the signals, using a technique called interferometry. When you combine signals from telescopes thousands of kilometers apart, you effectively create a telescope as large as the distance between them. The resolution, the ability to see fine detail, depends on the telescope's size. Bigger telescopes see finer details. And if your telescope spans the entire planet, well, then you can resolve very fine details indeed. The goal? To see the unseeable, a shadow against hot gas. Sagittarius A star doesn't emit light. Its event horizon is dark, invisible, a region where space-time curves so severely that light cannot escape. But the hot gas swirling around it does emit light, glowing brightly in radio wavelengths. And if you look carefully enough, with precise enough instruments, you should see the black hole's shadow silhouetted against that glowing gas. A dark circle where no emission reaches us, surrounded by a bright ring of radiation from the accretion disk. The photon ring, where light orbits just outside the event horizon before spiraling in or escaping outward. Einstein's equations predict exactly what this shadow should look like. The size, the shape, the asymmetry caused by the black hole's rotation and the motion of gas around it. For decades, scientists produced simulations showing what observers should see if they could ever achieve sufficient resolution. Now they were going to try. The angular size of Sagittarius I star from Earth is 52 microarcseconds. That's the size of the shadow as viewed from our perspective. Let's put that in human terms. Since microarcseconds means approximately nothing to most people, imagine a donut sitting on the surface of the moon. Not a building-sized donut, not a car-sized donut. A regular donut, the kind you'd buy at a bakery, maybe 10 centimeters across. Now imagine trying to see that donut's hole from Earth, 384,000 kilometers away. That's the challenge. That's the angular resolution required. It's absurd. The laws of physics, specifically the diffraction limit, prevent any single radio telescope on Earth from resolving such fine detail. The wavelength is too long, the dish is too small, the universe doesn't allow it. You could build the largest single radio dish imaginable, and it still wouldn't be enough. Unless you combine multiple telescopes spread across the entire planet, using interferometry to synthesize an effective aperture the size of Earth itself. Then, maybe, just maybe, you could resolve 52 microarc seconds. Maybe you could see the shadow. No single telescope could resolve that, but a planet-sized one could. This wasn't new technology exactly. Interferometry had been used in radio astronomy for decades, but applying it to achieve planetary scale resolution, coordinating observations across 8 sites, processing the enormous amounts of data involved, making everything work simultaneously. That was new. That was pushing the technique to its limits. The data collection alone presented challenges. Each telescope generated petabytes of information per night, too much to transmit over the internet. Instead, the data was recorded on hard drives, actual physical hard drives that had to be shipped to processing centers. In some cases, it was literally faster to fly the hard drives across the ocean than to transmit the data electronically. The South Pole telescope's data had to wait months until the Antarctic winter ended, and planes could fly in to retrieve the drives. You can't ship hard drives during Antarctic winter. The continent is isolated, cut off, inaccessible. So the data sat there, waiting patiently at the bottom of the world until spring arrived and transportation became possible. Modern astronomy sometimes involves waiting for seasonal shipping windows. It's oddly mundane given the cosmic nature of what's being studied. But that's science. Sometimes the cutting edge of research is limited by airline schedules and cargo logistics. Once all the data arrived at processing centers, the real work began, combining signals from 8 telescopes, accounting for Earth's rotation, atmospheric interference, instrumental effects, calibrating, correcting, processing. The computational effort was enormous, requiring specialized algorithms and powerful computers running for months. But if it worked, if everything came together properly, they produced the first image of Sagittarius A star's shadow, the first direct visual evidence of the event horizon at the center of our galaxy, the monster in our backyard made visible at last. Not visible to our eyes, of course. Radio wavelengths aren't something we perceive directly, but translated into images we could see, false-colored to show intensity, processed to reveal structure, an image, a photograph, of sorts, of darkness outlined by light. They were going to photograph a black hole, our black hole, the heart of home. After decades of watching stars orbit it, after years of preparation, they were finally going to see it. Or rather, they were going to see its shadow, the next best thing to seeing something that cannot be seen. Unlike M87 star, Sagittarius A star changes appearance minute by minute. This presented a problem, not an insurmountable one, but definitely a problem. M87, the supermassive black hole at the center of the galaxy, Messier 87, is massive. 6.5 billion solar masses. It's so large, so enormous, that material takes hours or days to orbit near its event horizon. When the Event Horizon Telescope imaged M87 in 2017, the black hole essentially held still during observations. It changed, certainly, but slowly enough that the team could treat it as stable, could combine observations taken over several nights, could build a single coherent image without worrying too much about the target shifting and changing while they watched. Sagittarius A star, different story entirely. At 4 million solar masses, it's much smaller than M87, more than 1,000 times less massive. And that size difference matters because the orbital period scales with mass. Near Sagittarius A star's event horizon, material orbits fast, very fast. A blob of hot gas circling just outside the photon ring completes an orbit in minutes, not hours. Hotspots in the accretion disk orbit the black hole every few minutes. Bright regions, places where the gas is particularly hot or dense, move around the black hole's equator at tremendous speeds. These hotspots appear in the emission, drift across the field of view, disappear, and reappear elsewhere. The entire structure shifts and changes on timescales shorter than a single observation run. This means the image is constantly shifting, like photographing a fidgeting subject. Imagine trying to take a long exposure photograph of someone who won't hold still. Someone who keeps moving, changing position, shifting their expression. The result is blur. Motion smear, a photograph that captures movement but loses definition. Now imagine the person you're photographing is 27,000 light-years away, visible only in radio wavelengths, and requires a planet-sized telescope to see it all. And they're fidgeting on timescales of minutes. That's the challenge Sagittarius A star presented. The variability wasn't unexpected. Simulations had predicted it. Astronomers knew the black hole would change rapidly. But knowing something theoretically and dealing with it practically are different things. The team had to develop new techniques, new ways of processing data, new algorithms that could handle a target that refused to hold still. They couldn't just average observations taken over a single night the way they did with M87 star. By the time several hours passed, Sagittarius I star's appearance would have changed completely. The hotspots would have moved. The brightness distribution would have shifted. Averaging those observations together would blur everything into an incoherent mess. The EHT captured thousands of frames over years, averaging them into a single portrait. Not a simple average. A sophisticated statistical analysis that looked for persistent features, structures that remained consistent even as the details changed. The fundamental shape, the shadow, the photon ring, the overall geometry stayed the same. But the fine structure, the specific distribution of brightness, varied constantly. So the team developed algorithms that could separate the persistent structure from the variable details, that could identify what stayed constant and what shifted minute to minute, that could extract the underlying shape from thousands of observations that each showed something slightly different. It took years, literally years of analysis, of testing different approaches, of running simulations to validate techniques, of processing and reprocessing the data. The observations happened in 2017. The image wasn't released until 2022. 5 years of work to transform petabytes of raw data into a single portrait of our galaxy's heart. Compare that to M87 star. That image was released in 2019, just 2 years after the observations. Sagittarius A star required more than twice as long, not because it's harder to observe, it's actually closer and brighter in some ways, but because it's harder to process, because the variability demanded more sophisticated analysis. Astronomers sometimes joke that Sagittarius A star is an uncooperative subject, won't hold still for the camera, keeps fidgeting, makes the photographer's job unnecessarily difficult. It's funnier when you consider that we're talking about a 4 million solar mass black hole, an object with gravity so intense that light cannot escape, described as if it's a restless child. But the description fits. If M87 star is the patient subject, sitting still and making everything easy, Sagittarius A star is the one who can't stop moving, Who makes you take hundreds of photos hoping one comes out clear? Who tests your skills as a photographer? On May 12, 2022, the team released the first image ever of Sagittarius A star. 7 simultaneous press conferences around the world, the second black hole photograph, but this time it was ours, not a distant giant in a galaxy 55 million light-years away. Our black hole, the heart of our home, the thing around which we orbit. The image appeared on screens, an orange ring glowing against darkness, smaller than M87's ring, more turbulent looking, more dynamic even in the still image, but unmistakable. The same pattern predicted by Einstein's equations, the same structure shown in simulations for decades. The photon ring, where light orbits at the edge of stability, caught between escaping and falling in. The shadow, where the event horizon silhouettes against that ring, a dark circle marking the boundary of the knowable. And there, visible in the image, hints of a symmetry that come from the black hole's spin, from matter flowing inward, from the dynamics of accretion. The ring wasn't perfectly circular. It had brighter regions and dimmer regions, structure that hinted at the complex processes happening in the accretion disk. Material falling in from different directions, magnetic fields twisting through the plasma, the rotation of the black hole dragging space-time around it. All of this encoded in the pattern of brightness around the shadow. After 50 years of knowing Sagittarius A star existed, after more than 20 years of watching stars orbit it, after years of building and coordinating the Event Horizon Telescope, after 5 years of processing the most challenging dataset in observational astronomy, we finally saw it. The monster in our backyard, no longer invisible, no longer just mathematics and orbital mechanics and theoretical predictions. There, visible, real, photographed in radio wavelengths and presented to the world. Not the black hole itself, of course. That remains invisible, hidden behind its event horizon, forever beyond direct observation. But its shadow, the outline it casts against the glowing accretion disk, the fingerprint it leaves on the light around it. Close enough, after all the decades, after all the work, after all the patience and analysis and coordination, close enough. We couldn't see the unseeable, but we could see what the unseeable does to everything around it. We could photograph its absence, its shadow, its effect on light. And in that shadow we found the heart of home, the center of everything we know, the anchor that holds the galaxy together, silent, dark, invisible to our eyes, but there, unmistakably there, proven beyond doubt, photographed at last. Even darkness can be home, especially when that darkness finally lets itself be seen. Sagittarius A star has an accretion disk of hot plasma spinning around it. Not a solid disk like a vinyl record or compact disk, a disk of gas and dust, heated to enormous temperatures, orbiting the black hole in a complex turbulent flow, material spiraling inward, gradually losing energy, slowly making its way toward the event horizon. The disk isn't smooth or uniform, it's lumpy, clumpy, full of structure. Magnetic fields thread through it. Turbulence creates eddies and hot spots. Density varies from place to place. Some regions are hotter and brighter, others are cooler and dimmer. The whole thing churns and shifts on timescales of minutes to hours. Think of it as a cosmic whirlpool, material falling toward the drain, circling as it goes down, heating up through friction as particles rub against each other and magnetic fields tangle and snap. The closer to the black hole, the faster the orbital speed, the stronger the heating, the brighter the emission. The disk glows mostly in radio and X-ray wavelengths, invisible to our eyes. If you could somehow transport yourself to the galactic center and look at Sagittarius A star with human eyes, you wouldn't see the accretion disk at all. It emits almost nothing in visible light. You'd see the stars, certainly, millions of them crowding the sky, but the black hole and its disk would remain invisible, detectable only with instruments sensitive to different wavelengths. Radio telescopes see it clearly, a bright source of emission, variable and complex. X-ray telescopes see it too, catching the higher energy photons released when gas reaches truly extreme temperatures. But visible light? The disk is too hot or too cool, or perhaps both in different regions, to emit much in the narrow band of wavelengths our eyes perceive. So we observe it in wavelengths we cannot see, translate those observations into images and graphs and data, and build understanding from electromagnetic signals our biology never evolved to detect. Magnetic fields in the disk twist and snap, launching bursts of energy. This is where things get violent, or at least as violent as Sagittarius A star gets. Magnetic field lines carried along with the orbiting plasma get tangled, stretched, twisted into complex geometries, and eventually, when the stress becomes too great, they snap and reconnect. Magnetic reconnection, the process is called, the same phenomenon that powers solar flares on the sun, but scaled up to the environment around a supermassive black hole. When fields reconnect, they release tremendous energy. Particles get accelerated to high speeds, radiation bursts forth, the disk suddenly brightens in X-rays or radio waves. These events are unpredictable. They happen when they happen, following the chaotic dynamics of turbulent magnetized plasma. You can't schedule them, you can't predict them, you can only watch and wait, hoping to catch one with instruments pointed in the right direction at the right time. Occasionally, the black hole flares hundreds of times brighter for a few hours. Not regularly, not predictably, just occasionally, when conditions align, when enough gas falls in or when magnetic fields reconnect in just the right way. The X-ray emission suddenly spikes, the galactic center blazes in high-energy light, and then, hours later, it settles back down to its usual faint background. Most days, Sagittarius A star is quiet, dormant, emitting faint radio waves and occasional X-rays, but nothing dramatic. It sits there at the galactic center, anchoring everything, holding stars in their orbits, doing its gravitational work without fanfare. Background noise in the cosmic symphony. Then, unpredictably, it flares. The emission brightens by factors of hundreds. For a few hours, the black hole becomes one of the brightest X-ray sources in the galactic center. Then, it fades again, returning to quiescence, as if nothing happened. These flares may come from blobs of gas crossing the event horizon. That's one theory. Perhaps a clump of material denser than its surroundings makes final plunge. As it falls inward, it heats to enormous temperatures, releases a burst of energy, and disappears beyond the horizon. The last scream of matter before crossing the point of no return. Or perhaps magnetic reconnection causes the flares. Tangled field lines suddenly snap, release energy, accelerate particles, produce bright emission, similar to solar flares but vastly more energetic. The plasma around Sagittarius A star is magnetized, turbulent, full of stored energy waiting to be released. Or perhaps it's some combination. Gas falling in triggers magnetic instability. Magnetic reconnection accelerates gas infall. The processes feed each other in complex ways that simulations are only beginning to untangle. We're not certain. We observe the flares. We measure their brightness and duration and spectrum. We watch them happen in real time when we're lucky enough to be observing. But understanding exactly what triggers them, what physical process produces each flare, remains an active area of research. The black hole doesn't explain itself. It just flares occasionally on its own schedule, keeping astronomers guessing. Another reminder that even after decades of study, after measuring orbital mechanics and photographing shadows and testing relativity, Sagittarius A star still holds surprises. It's not completely understood, not fully predictable, not reduced to a simple set of equations we can solve perfectly. It's a natural system, chaotic and complex, doing what it does for reasons we're still working out. And there's something wonderful about that. Something satisfying about knowing that the monster in our backyard, even after all the work to understand it, remains partially mysterious, keeps flaring unpredictably, keeps reminding us that nature doesn't give up all its secrets easily. We watch, we measure, we build theories, and occasionally, when the black hole flares, we get new data to puzzle over, new clues to what's happening in the extreme environment where space-time curves toward infinity and matter takes its final journey before disappearing forever. NASA's Chandra and New Star observatories monitor these flashes continuously. Well, not continuously in the literal sense. Telescopes need maintenance, they observe other targets, they're not exclusively dedicated to watching Sagittarius A star, but regularly, frequently. Chandra, NASA's X-ray observatory, checks in on the galactic center often. New Star, the Nuclear Spectroscopic Telescope Array, does the same, watching for high-energy X-rays. Between them, they catch many of the flares. Not all of them. You can't catch everything when your target is 27,000 light-years away, and your telescopes are in Earth orbit with their own schedules and constraints. But enough. Enough to build a catalogue of flares, to study their properties, to understand their typical brightness and duration. The observatories have been watching for years, accumulating data, building a record of Sagittarius A star's behavior over time. Every flare observed adds to that record, helps refine models of what's happening in the accretion disk, contributes to our understanding of how black holes feed. The black hole's rotation probably drives much of this activity. Black holes rotate almost certainly. They form from rotating material, collapsing gas clouds, merging stellar remnants. Whatever process created them involved rotation. And because angular momentum is conserved, the resulting black hole inherits that rotation. For Sagittarius A star, we think it's rotating, though measuring the spin of a black hole is surprisingly difficult. You can't watch it turn. You can't time the rotation directly. You have to infer spin from indirect evidence. The shape of the accretion disk, the properties of X-ray emission, subtle effects on orbiting material. The rotation affects everything near the event horizon. A rotating black hole drags space-time around with it, creating what's called the ergosphere, a region where space itself is forced to rotate, where nothing can remain stationary even if it wanted to. Material in the accretion disk feels this drag, its orbits influenced by the spinning space-time. This rotation probably contributes to the flaring, to the disk's turbulence, to the magnetic field dynamics. The exact mechanisms are still being worked out, but rotation matters. It shapes the environment around the black hole, influences how material falls in, affects the emission we observe. Yet Sagittarius A star is a remarkably slow eater, consuming only a tiny fraction of available gas. Here's the paradox. The black hole sits at the center of the galaxy, surrounded by gas, dust, and stars. Material is available. The gravitational pull is enormous. You'd expect constant feeding, continuous accretion, a bright and active galactic center. But no, Sagittarius A, star barely eats. It consumes perhaps 1/10,000th of a solar mass every million years. That's nothing, a rounding error. Astronomically insignificant, literally. For comparison, quasars in the early universe, supermassive black holes actively feeding, can consume several solar masses per year. Per year, not per million years. Sagittarius A star is underfed by a factor of millions compared to those actively feeding giants. Astronomers call it underfed compared to quasars in distant galaxies. It's almost disappointingly quiet. The galaxy's centre should be bright, active, dramatic, and it is, compared to empty space. But compared to what supermassive black holes can do when they really feed, when they're gorging on material, Sagittarius A star is barely snacking. Why? Partly because most of the nearby gas is in stable orbits. It's not falling inward, but orbiting peacefully, held up by angular momentum. The gas circles the black hole the way Earth circles the Sun. Stably, without falling in. Some of it gradually spirals inward through friction and magnetic effects, but slowly. Very slowly. Partly because the accretion flow is inefficient, most of the gas that starts falling inward gets heated, very heated, and that heating gives it energy, makes it move faster, sometimes gives it enough energy to escape the black hole's pull entirely. The gas blows outward rather than falling in. Only a fraction actually makes it to the event horizon. And partly because there just isn't that much loose material available anymore. The galactic centre's gas has been processed, consumed or blown away over billions of years. What remains is spread out, orbiting stably, not particularly inclined to fall in. There's not a constant supply of fresh material raining down on the black hole. So, Sagittarius A star sits mostly hungry. Occasionally something falls in. A gas cloud wanders too close, loses angular momentum, spirals inward. The black hole flares briefly, then back to quiescence, back to barely eating, back to sitting quietly at the galactic centre doing its gravitational work without consuming much. Even so, its occasional hunger pangs ripple across the galactic core. When it does flare, when it does briefly brighten, the effect is noticeable across the nuclear stellar cluster. The X-rays illuminate nearby gas clouds. The emission affects the ionization state of surrounding material. The flare becomes an event, observable and measurable, even if it lasts only hours. The black hole's starvation diet has implications. If it were feeding more actively, the galactic center would look completely different. Brighter, more violent, more hostile to nearby stars. The radiation environment would be harsher. Material would be blown outward at tremendous velocities. We might see jets, narrow beams of particles and energy shooting out perpendicular to the accretion disk. But we don't see that. Sagittarius I star is calm, underfed, quiet, and that quietness has shaped the evolution of our galaxy, has allowed stars to form and thrive near the center, has created an environment where patient observation is possible. The monster in our backyard turned out to be a polite monster, barely eating despite the invitation, holding everything together through gravity alone, not through violent feeding. The silence at the center remains mostly silent, occasionally interrupted by brief flares that remind us something is there, still active, still consuming material, just very, very slowly. Even darkness can be home, especially when the darkness minds its manners and doesn't eat too much. Evidence suggests Sagittarius I star was much brighter millions of years ago. Not speculation, not guesswork. Evidence. Multiple lines of it, pointing to the same conclusion, that the quiet, underfed black hole we observe today was once significantly more active, perhaps not quasar-bright, not a blazing beacon visible across the universe, but brighter than now, more active, feeding more vigorously. The evidence comes from several sources, from gas clouds that still glow with energy they absorbed long ago, from structures in the galaxy that require more powerful radiation than Sagittarius A star currently produces, from patterns in the interstellar medium that suggest past outbursts. The galactic center remembers its more violent history, even if the black hole has calmed down since. Gamma-ray bubbles above and below the galactic plane mark ancient outbursts. These structures, discovered in 2010 by NASA's Fermi Gamma-ray Space Telescope, are enormous. Not planet-sized, not star system-sized. Galaxy-sized. Each bubble stretches 25,000 light-years from the galactic center. 25,000 light-years in each direction, perpendicular to the galactic plane. These Fermi bubbles extend above and below the disk like cosmic earlobes. If earlobes were made of high-energy gamma rays and stretched halfway across the galaxy, they glow faintly, visible only to instruments sensitive to the highest energy light. You can't see them with your eyes, obviously, but they're there, symmetrical structures reaching out from the galactic center in opposite directions. These Fermi bubbles stretch 25,000 light-years each direction, half the galaxy's width. That's not a typo, not an exaggeration. Each bubble, from the galactic center to its farthest extent, spans roughly half the visible width of the Milky Way's disk. They're huge. Absurdly huge. The kind of structure that makes you reconsider the scale you think on. They may be fossil remains of powerful jets from the black hole. Jets are what happen when black holes feed actively. Material doesn't all fall in. Some gets caught in magnetic fields, accelerated to tremendous speeds, and shot outward in narrow beams perpendicular to the accretion disk. These jets can carry enormous energy, ploughing through surrounding gas, creating huge bubbles of hot material. The Fermi bubbles might be remnants of such an event, evidence that Sagittarius A star once launched jets, once fed more vigorously, once was active enough to create structures visible halfway across the galaxy. The bubbles themselves are old, perhaps millions of years old, possibly older. They're not being actively powered now. They're just there, fossils of ancient violence, glowing faintly in gamma rays because they still contain high-energy particles and radiation. What triggered the feeding episode that created them? We don't know. Perhaps a large gas cloud wandered too close to the galactic center, lost angular momentum, and fell in. Perhaps a star got disrupted by tidal forces, and its debris fed the black hole. Perhaps something else entirely happened, some event we haven't identified yet. Whatever it was, it's over now. The black hole has returned to its current underfed state. The jets, if they existed, have shut off. But the bubbles remain, testament to the galactic center's more active past. X-ray echoes in nearby gas clouds show flashes from a centuries-old eruption. These are different from the Fermi bubbles. Smaller scale, more recent. Within the past few hundred years, Sagittarius A star apparently flared quite brightly. Not for hours, like its current occasional flares. For longer, perhaps days or weeks. Bright enough that gas clouds dozens of light-years away absorbed the X-rays, got ionized, and still glow from that absorbed energy. X-ray echoes work like sound echoes but with light. The black hole flares. Light travels outward at light speed. Nothing surprising there. Some of that light hits gas clouds dozens of light-years from the black hole. Those clouds absorb the energy, get heated, start glowing themselves, and because they're farther from us than the black hole, their light takes longer to reach us. So we see the gas clouds lighting up centuries after the original flare. The light from the flare itself has long since passed Earth, travelling onward into space. But the reflected light, the echo from distant gas clouds, arrives later. By studying these echoes, astronomers can reconstruct what the original flare must have been like, how bright, how long, how much energy it released. And the answer is pretty bright. much brighter than Sagittarius A star's current flares. Not a gentle burp, but a substantial outburst. Something fell in, something significant, and for a brief period, cosmically speaking, the galactic centre blazed far more brightly than it does now. Then it faded. The outburst ended. The black hole returned to quiescence. But the gas clouds remember, glowing faintly with absorbed energy, visible to X-ray telescopes as echoes of violence that occurred when Enlightenment-era astronomers were first mapping the stars. The galactic centre has a history, a story of varying activity, periods of quiet interrupted by outbursts, sometimes small flares lasting hours, sometimes larger eruptions lasting weeks, sometimes millions of years ago episodes violent enough to create bubbles stretching halfway across the galaxy. Sagittarius A star isn't constant. It's variable over timescales from minutes to millions of years, currently underfed and quiet, but capable of more, capable of feeding when material becomes available, capable of brightening, flaring, creating structures that last long after the feeding ends. We're observing it during a quiet phase, a fortunate time to be studying it, actually. If it were as active as it apparently was millions of years ago, the galactic centre would be a much harsher environment. The radiation would be more intense. Observations would be more challenging. Life in the galaxy might be more difficult. But it's quiet now, polite, well-behaved, and the echoes of its past violence remain visible, reminding us that even darkness has history, that even silence can be interrupted, that the monster in our backyard wasn't always so well-mannered. Today, Sagittarius A star is about 100 times dimmer than similar black holes. Not slightly dimmer, not a bit quieter, 100 times dimmer. Take a typical supermassive black hole at the centre of a similar-sized galaxy, measure its output in X-rays and radio waves and other wavelengths, then divide by 100. That's roughly what Sagittarius A star produces. This isn't criticism. The black hole isn't underperforming. It's just underfed, as we discussed. And that underfeeding has profound implications for everything around it, including us, 27,000 light-years away in the outer spiral arm. Other galactic centres are brighter, more active, more violent. Their black holes feed more vigorously. They consume gas at higher rates. They produce more radiation, launch stronger jets, create harsher environments for nearby stars. Some are so bright they're visible across billions of light-years, outshining entire galaxies. Quasars, we call them, though technically a quasar is just an actively feeding supermassive black hole viewed at the right angle. Sagittarius A star could be brighter. The mass is there. 4 million solar masses is substantial. If material were available, if gas clouds regularly fell in, if the feeding were more efficient, our galactic centre could be dramatically more luminous. It has the potential, it just lacks the fuel, or at least lacks fuel in a convenient form that actually makes it to the event horizon. If visible to our eyes, it would barely flicker compared to surrounding stars. Even if you could somehow clear away all the dust between us and the galactic centre, even if you had perfect visibility and looked in visible wavelengths, Sagittarius A star's accretion disk would be dim, faint, easy to overlook among the millions of stars crowding the nuclear cluster. The stars would dominate. Their combined light would wash out the faint glow from the accretion disk. You'd need to block out the starlight, to observe very carefully, to know exactly where to look before you'd notice the black hole at all. It's not invisible exactly, but it's not prominent either. Which is odd when you think about it. The most massive object in the region, the gravitational anchor for 400 billion stars, and it barely registers visually. But that's the nature of underfed black holes. They don't announce themselves unless they're actively consuming material. Its calmness lets life thrive in the outer arms of our galaxy. This matters. This matters quite a lot, actually. We exist because Sagittarius A star is quiet. Not metaphorically, literally. If our galactic center were as active as some others, if it were feeding voraciously and producing intense radiation, the entire galaxy would be affected. The radiation environment would be harsher everywhere, cosmic rays more abundant, high-energy particles streaming outward from the galactic center, affecting star formation, potentially disrupting planetary atmospheres, creating conditions less hospitable to life. Not immediately lethal, perhaps. Distance helps. 27,000 light-years provides substantial shielding. But chronic exposure over billions of years, that would matter. Evolution happens in response to environmental conditions. Change those conditions significantly, and evolution takes different paths. Complex life might struggle more. Intelligence might be less likely to develop, or might develop differently, adapted to higher radiation environments. Too much activity, and Earth might bathe in harmful radiation. Again, not enough to sterilize the planet instantly. We're far enough away that distance provides protection, but enough to raise background radiation levels. Enough to increase mutation rates. Enough to make the evolution of complex, long-lived organisms more challenging. Would we exist at all? Hard to say. The question ventures into speculation, but the calm at the center certainly hasn't hurt our prospects. The Sun orbits peacefully through the galaxy. Earth orbits peacefully around the Sun. And at the center of everything, Sagittarius A star sits quietly, barely eating, producing minimal radiation, letting the rest of the galaxy go about its business undisturbed. Our galactic center's quietude is a cosmic gift, one we rarely acknowledge. We don't think about it much, don't celebrate it, don't mark it on calendars or teach it in schools beyond mentioning that there's a black hole at the galactic center. But that black hole's restraint, its underfed state, its dormancy, these are conditions that helped make our existence possible. Other civilizations, if they exist, in galaxies with more active centers, might not be so fortunate. They might deal with higher radiation backgrounds, more cosmic rays, more energetic outbursts from their galactic centers, more challenges to overcome. We got lucky. We're in a quiet galaxy with a quiet center. And that quietness, that absence of violent activity, that restraint in feeding, has shaped our existence in ways we're only beginning to appreciate. The silence at the center is part of why we're here to wonder about it, part of why Earth remained habitable for billions of years, part of why complex life had time to evolve, why intelligence emerged, why we can build telescopes and study the very black hole whose calmness contributed to our existence. It's a nice cosmic irony. The monster in our backyard turned out to be exactly the kind of monster you want in your backyard, the quiet kind, the polite kind, the kind that minds its own business and doesn't bother the neighbors with excessive radiation or violent outbursts. The kind that holds everything together through gravity alone, without making a fuss about it, without demanding attention, without creating conditions that would make life difficult for everyone else. We exist in its gravitational field, orbit under its influence, evolved in a galaxy it helped shape. And the fact that it's been quiet for most of that time, that's not just convenience, that's fortune. Cosmic scale fortune that we inherited by the simple luck of forming in this galaxy, rather than another. Even darkness can be home, especially when the darkness is considerate enough to stay quiet and let life flourish in the outer neighborhoods. Sagittarius I star influences star formation near the galactic core. Not through direct intervention, the black hole doesn't reach out and create stars, but through gravity, through radiation, through its mere presence as a 4 million solar mass object at the centre of everything. The environment near the galactic centre is shaped by the black hole, and that shaping affects where and how stars can form. Star formation requires specific conditions: dense molecular clouds, sufficient cooling so gravity can overcome thermal pressure, relative stability so collapsing regions aren't disrupted before stars finish forming. Near the galactic centre, these conditions exist, but they're modified by Sagittarius A star's influence. The black hole's gravity affects cloud dynamics. Its occasional radiation affects cloud chemistry. Its tidal forces limit how close clouds can approach before being torn apart. All of this shapes the star formation environment in ways that don't occur farther out in the galaxy, where the black hole's influence is weaker. Its gravity sculpts giant molecular clouds hundreds of light years away. Gravity weakens with distance, certainly, but it never goes to zero. Even hundreds of light years from Sagittarius A star, its gravitational influence remains significant compared to other sources of gravity at the galactic centre. Giant molecular clouds, vast accumulations of gas and dust, the birthplaces of stars, feel the black hole's presence. Their orbits are shaped by it. Their motions through the galactic centre are influenced by that massive central object. They can't ignore it, can't treat it as negligible, even at hundreds of light years distance. The clouds orbit in patterns determined partly by the black hole's gravity, partly by the distributed mass of millions of other stars. They follow complex paths through the galactic centre, sometimes approaching closer, sometimes drifting farther out. Their trajectories shaped by the gravitational architecture of the entire region. This gravitational shaping affects where stars form. Clouds in certain orbits get compressed when they pass through dense regions, triggering star formation. Clouds in other orbits remain stable, dormant, not quite reaching the density needed for collapse. The black hole doesn't directly create stars, but its gravity shapes the environment where star birth happens or doesn't happen. Stellar winds and supernovae from nearby stars feed it fresh material. The galactic centre is crowded, stars live close together, and stars, particularly massive ones, produce winds, streams of particles blown off their surfaces by radiation pressure. When massive stars die as supernovae, they scatter material across the region. All of this feeds back into the environment. Some of that material eventually drifts towards Sagittarius A star, not quickly, not in straight lines, but over time through complex dynamics involving collisions, friction, magnetic fields, and orbital decay. Some fraction of the gas shed by stars makes its way inward. The black hole gains mass slowly, fed by the stellar activity around it. It's a feedback loop. Stars form near the galactic centre. They live, producing winds and radiation. Some explode as supernovae, enriching the interstellar medium with heavy elements. That enriched material becomes available for the next generation of stars, or drifts inward toward the black hole, or gets blown outward by energetic events. The cycle continues, has continued for billions of years, shaping the galactic centre's evolution. Magnetic fields link the black hole to surrounding gas streams. The region around Sagittarius I star isn't just gravitationally complex, it's magnetically complex too. Magnetic fields thread through the gas, connecting different regions, channeling material along field lines, influencing how gas moves and where it goes. These fields aren't static, they evolve, they twist as gas orbits the black hole. They get amplified by the rotation of the accretion disk. They snap and reconnect, launching flares. They interact with stellar winds and supernova remnants. The magnetic environment is dynamic, turbulent, constantly changing, and those fields connect the black hole to its surroundings. Material can flow along field lines. Energy can be transmitted through magnetic stresses. The black hole isn't gravitationally isolated. It's magnetically connected to gas clouds light years away, linked through invisible lines of force that guide material inward and channel energy outward. Its radiation ionizes gas tens of light years away, affecting cloud chemistry. Even though Sagittarius A star is underfed, even though it's much dimmer than it could be, it still produces radiation. X-rays from the accretion disk, radio waves from the hot plasma, occasional flares that briefly brighten everything, and that radiation travels outward, affecting surrounding material. Gas clouds tens of light-year away absorb this radiation. The high-energy photons knock electrons off atoms, ionizing the gas. Ionized gas behaves differently than neutral gas. It responds to magnetic fields. It conducts electricity. Its chemistry changes. Different reactions become possible. Different molecules can form or be destroyed. This affects star formation in subtle ways. The ionization state of a cloud influences its temperature and pressure. It affects how efficiently the cloud can cool, which affects whether gravity can overcome thermal pressure to trigger collapse. Sagittarius A star's radiation, even at its current low level, shapes the chemical and physical state of gas clouds throughout the inner galaxy. The black hole influences its environment through multiple channels simultaneously. Gravity shapes orbits and compresses clouds. Radiation ionizes gas and affects chemistry. Magnetic fields connect regions and guide material flow. Tidal forces limit how close things can approach. All of these work together, creating a complex ecosystem where the black hole, stars, gas, and magnetic fields interact continuously. It's not a simple system, not reducible to one or two effects. It's a genuine ecosystem, with feedback loops and complex interactions and emergent behaviors that aren't obvious from studying any single component alone. The galactic center is more than just a black hole surrounded by stars. It's a dynamic, interconnected environment where everything affects everything else. And at the center of it all sits Sagittarius I star, not controlling everything directly, not micromanaging star formation, just existing, massive and present, shaping the environment through its fundamental properties: gravity, radiation, magnetic coupling, the monster in our backyard quietly influencing everything around it while remaining invisible to our eyes. Even darkness can be home, especially when that darkness shapes the neighborhood and makes it livable for millions of stars. The central parsec of the Milky Way is among the most turbulent regions in the galaxy. A parsec is about 3¼ light years, not a huge volume by galactic standards, but not tiny either. Within that central parsec, a sphere about 6½ light years across, centered on Sagittarius A star. Conditions are extreme. Stars crowd together more densely than anywhere else in the galaxy. Gravitational interactions are common. Orbits shift and change. The radiation environment is harsher than in the outer spiral arms. Material orbits at tremendous speeds. And at the very center sits the black hole, dominating the gravitational landscape. Turbulent is perhaps an understatement. Chaotic might be more accurate, dynamic, complex, constantly changing. Not a calm, stable environment where things remain predictable over long timescales, but a place where conditions vary, where close encounters between stars happen occasionally, where the unusual becomes routine. Stars there orbit so fast that their lifespans are compressed by extreme conditions. Not their actual lifespans. Stars age according to their internal nuclear fusion rates, which don't particularly care about external conditions, but their effective lifespans in the region, how long they remain in stable orbits before something disrupts them. In calmer parts of the galaxy, stars orbit peacefully for billions of years. Their paths remain stable. They rarely encounter other stars closely. They just orbit generation after generation, never disturbed. But in the central parsec, close encounters happen more frequently. A star might drift too close to another star, or to Sagittarius A star, and get ejected from the region entirely, or drawn into a tighter orbit, or disrupted by tidal forces. The survival time in the central parsec is shorter than in the outer galaxy, not because stars burn out faster, but because the environment is more violent. Things happen, orbits change. Stars don't stay put as reliably. Some massive stars explode as supernovae, and their remnants spiral inward. Massive stars live fast and die young. They burn through their nuclear fuel quickly, a few million years for the most massive ones compared to billions of years for stars like the Sun. And when they exhaust their fuel, they explode. Supernovae are not subtle events. They release enormous energy, blow off the star's outer layers, scatter enriched material across the surrounding region. In the galactic center, some of that material remains bound to the central region. It doesn't escape entirely. Instead, it spreads out, cools, interacts with other gas, and eventually some fraction spirals inward towards Sagittarius A star. The black hole slowly gains mass from these events, not quickly. Supernovae don't donate all their material to the black hole. Most of the ejected gas stays in the general region, or escapes entirely. But some, over time, through complex orbital dynamics and friction and magnetic effects, makes its way inward, a slow trickle of enriched material, gradually feeding the black hole over millions of years. Over billions of years, the black hole acts as a galactic recycler. Think of Sagittarius A star as a cosmic recycling center, operating over geological timescales. No, longer than geological, cosmological timescales. Gas clouds drift inward, get disrupted, form stars. Those stars live and die. Some explode as supernovae, scattering enriched material. Some of that material falls toward the black hole. Some gets incorporated into new stars. The cycle repeats. Each iteration adds slightly to the black hole's mass while redistributing material throughout the galactic center. The black hole grows slowly but steadily, 4 million solar masses now, but it started smaller. How much smaller? Hard to say. Supermassive black holes probably formed in the early universe and have been growing ever since, fed by gas infall and occasional star captures over billions of years. The recycling shapes the galactic ecology. Heavy elements produced in stellar cores get dispersed by supernovae, then incorporated into new generations of stars. The black hole grows, the stellar population evolves, the gas chemistry changes as more heavy elements accumulate. Iron, carbon, oxygen, silicon, all the elements created in stars, scattered through the region, available for forming planets and eventually, if conditions permit, life. Without this recycling, without the continuous processing of material through stars and supernovae and accretion, the galactic center would be chemically primitive, mostly hydrogen and helium, the primordial elements from the Big Bang. But billions of years of stellar alchemy have enriched the region, created the chemical complexity necessary for interesting things like planets and eventually us. Everything that falls in eventually becomes part of its mass, shaping future evolution. Material that crosses the event horizon doesn't disappear in any meaningful sense. The mass and energy are conserved, added to the black hole's total. The black hole grows by exactly the amount that falls in. Information about what fell in, the specific arrangement of particles, the detailed structure, that might be lost. But the mass remains, increasing the black hole's gravitational pull affecting the orbits of everything around it. So in a sense, everything that ever fell into Sagittarius A star is still there, still contributing, still shaping the galactic center's evolution. The gas clouds, the stars that wandered too close, the supernova remnants that spiraled inward, all of it compressed beyond the event horizon, increasing the mass, strengthening the gravity, influencing the future. The black hole is both endpoint and engine. Endpoint because material that falls in is removed from the observable universe, gone from our perspective, but also engine because its gravity drives the dynamics of the region, shapes orbits, compresses gas clouds, triggers star formation indirectly. It's simultaneously the destination and the driver of the galactic center's evolution. It's a long, slow process, operating on timescales that dwarf human civilization, that dwarf human species, that approach the age of the universe itself. But it's constantly happening, material flowing inward, the black hole slowly growing, the stellar population evolving, the gas chemistry enriching, the galactic center changing gradually over billions of years. We observe a snapshot, a moment in that long evolution. Sagittarius A star as it is now in this brief period when humans exist and can build telescopes. But the processes we observe have been operating for billions of years before us, and will continue for billions of years after. The recycling continues, the black hole grows, the galactic ecosystem evolves, and at the center of it all, the monster in our backyard quietly processes material through gravity alone, patient and persistent, the ultimate recycler in a system that's been running since the galaxy formed. Even darkness can be home, especially when that darkness has been recycling the neighborhood for billions of years. Astronomers watched a gas cloud named G2 approach Sagittarius A star for years. Not decades, not centuries, years. The cloud was discovered in 2011, already on its way toward closest approach. Orbit calculations showed it would pass very close to the black hole in 2013. Close enough that tidal forces should tear it apart. Close enough that the resulting debris should fall into the black hole, producing a spectacular feeding event. The astronomical community took notice. It was a chance to watch a black hole feed in real time, to observe the process of accretion, to see what happens when material approaches the event horizon. Observatories around the world prepared. Telescope time was allocated. Everyone wanted to watch. It was predicted to be torn apart and devoured in 2013. The predictions weren't wild speculation. They were based on solid physics. Tidal forces, the difference in gravitational pull across an object, increase as you approach a massive body. G2 was a gas cloud, not a solid object. Gas clouds are fragile, held together weakly. The tidal forces from Sagittarius A star should stretch it, elongate it, tear it into a long stream of material. The stretched material should heat up as it falls inward. The black hole should flare dramatically. We might see the brightest activity from Sagittarius AY star in recorded history. It would be spectacular, educational, a once-in-a-lifetime observation of black hole feeding. The anticipation built for years. G2 was tracked carefully. Its orbit was refined. Its properties were measured. Predictions were made about what the flare would look like, how bright it would be, how long it would last. Papers were written. Observations were planned. The astronomical equivalent of everyone gathering around to watch something interesting happen. Instead, G2 survived its closest approach mostly intact, surprising everyone. Not completely intact. It was affected, stretched somewhat, heated a bit, but definitely not shredded into a long stream of material, raining down on the black hole. Definitely not producing the anticipated fireworks. It passed through closest approach in 2013, and emerged on the other side recognizable as G2. Still a coherent object, still moving along its orbit. Sagittarius A star remained quiet. No dramatic flare, no spectacular feeding event, just the usual occasional X-ray burps, nothing unusual. The black hole barely noticed G2's passage, or if it noticed, it didn't feel inclined to make a fuss about it. This was disappointing and fascinating in equal measure. Disappointing because everyone was hoping for a show. Fascinating because G2's survival meant the predictions were wrong, which meant our understanding of the situation was incomplete, which meant there was something interesting to figure out. This suggests G2 might hide a star inside its dusty shroud. That's the leading theory now. G2 isn't just a gas cloud, it's a star surrounded by a dusty envelope. The star provides gravitational binding, holds the material together against tidal forces. When G2 approached Sagittarius A star, it was the star's gravity holding everything together, not just the weak self-gravity of a gas cloud. This would explain why G2 survived when predictions said it shouldn't. The calculations assumed a pure gas cloud with no internal support. But a star changes everything. Stars are dense, gravitationally bound objects. They can survive tidal forces that would rip apart a diffuse gas cloud. The dusty envelope might get stretched and disturbed, but the star underneath remains intact. The star hypothesis isn't proven yet. We can't see through the dust to confirm there's a star inside, but it fits the observations. It explains why G2 survived. It suggests that what appeared to be a simple gas cloud was actually something more complex, more interesting, more resilient. The survival taught us that the environment near Sagittarius AY star is more complex than models predicted. Not just more complex in detail, but fundamentally more complex. The region near the black hole isn't empty space with occasional gas clouds drifting through. It's populated with objects we don't fully understand yet. Dust-shrouded stars, perhaps. Gas clouds with internal structure. Material flows more complicated than simple radial infall. G2 forced astronomers to reconsider their models, to refine predictions, to acknowledge that watching a gas cloud approach a black hole for the first time teaches you something, even if, especially if, the outcome isn't what you expected. The anticipated feast didn't happen. The black hole didn't flare dramatically, but the observation was still valuable. Science progresses through surprises as much as through confirmations. G2's survival said something important about the galactic center. Environment, about the objects orbiting there, about how material approaches Sagittarius A star. And it reminded everyone that nature doesn't always cooperate with predictions, that the universe has a way of being more interesting, more subtle, more complex than our models anticipate, that sometimes the most important observations are the ones where nothing dramatic happens, because that tells you your understanding needs adjustment. G2 is still out there, continuing its orbit, moving away from closest approach now. It'll return eventually. Orbital mechanics guarantees that. Maybe next time, with better models and better understanding, predictions will be more accurate. Or maybe G2 will surprise us again. That's the thing about observational astronomy. You watch what actually happens, not what you think should happen. The monster in our backyard declined the meal, polite as ever, and in that refusal taught us something about the complexity of its neighborhood, about the objects orbiting nearby, about the difference between what we predict and what actually occurs when you watch carefully. Even darkness can be home, especially when that darkness keeps surprising us with its complexity. If Sagittarius A star ever feeds on a massive cloud, it could flare dramatically. Not could in the sense of maybe, possibly, if conditions align perfectly. Could in the sense that the physics allows it, that the black hole is capable of it, that we've seen other black holes do exactly this when substantial material falls in. Right now, Sagittarius A star is underfed. We've established that. It barely snacks. But that's a function of available material, not capability. If a truly massive gas cloud, something with hundreds or thousands of solar masses, wandered too close, lost angular momentum, and fell inward, the black hole would feed, and the feeding would be visible across the galaxy. Such an event would outshine all other sources in the Milky Way core. Not slightly brighter, not moderately more luminous. Outshine. The accretion disk would blaze in X-rays. The black hole would become one of the brightest objects in the entire galaxy for the duration of the feeding event, possibly visible in wavelength beyond X-rays, maybe even optical if the flare were intense enough. How long would it last? Hard to say. Depends on how much material falls in, how quickly, how efficiently the accretion process converts mass to radiation. Could be weeks, could be months, could be years if the cloud were massive enough and the infill process gradual enough. Observatories would definitely notice. Every telescope capable of viewing the galactic center would turn that direction. Papers would be written, data would be collected. It would be the astronomical event of the decade, possibly the century. A chance to watch a supermassive black hole feed vigorously in real time in our own galaxy, close enough to study in detail. Has it happened before? Almost certainly. The Fermi bubbles suggest past episodes of vigorous feeding. The X-ray echoes indicate more recent outbursts. Sagittarius A star has fed dramatically before. It will feed dramatically again. The question isn't if, but when. The black hole grows slowly as it feeds, gaining perhaps 1 solar mass per million years. At its current feeding rate, that's the growth rate, 1 solar mass per million years. Sounds substantial until you remember the black hole already contains 4 million solar masses. It would take 4 million years to grow by just 1/10,000th of its current mass. Cosmic timescales, extremely slow by human standards, imperceptibly slow by observational standards. You can't watch the black hole grow. It gains mass far too gradually. But over billions of years, over the lifetime of the galaxy, it adds up. In the distant future, it could reach tens of millions of solar masses. If the feeding rate stays constant, which it won't, but for the sake of estimation, Sagittarius A star could double its mass in 4 million years. Quadruple in 8 million. Grow to 10 times its current mass in 40 million years. That's still less than 1% of the galaxy's age. The Milky Way is about 13 billion years old. Sagittarius A star has had plenty of time to grow, and will have plenty more time ahead. Eventually, given enough time and enough material, it could reach tens of millions of solar masses, maybe even 100 million, if conditions favor continued growth. But growth isn't guaranteed. It depends on available material. Gas clouds need to be present, need to lose angular momentum, need to fall inward. Stars need to wander too close occasionally. The feeding has to continue. If the galactic center runs out of conveniently located material, growth slows or stops. Still, the trend over billions of years has been growth. Sagittarius A star is more massive now than when it formed, and it will likely be more massive in the future, barring some catastrophic event that disrupts the galaxy entirely. One day, perhaps 4 billion years from now, Andromeda's black hole and ours will merge. This isn't speculation, it's prediction based on current measurements. The Andromeda galaxy and the Milky Way are approaching each other at about 110 kilometers per second. They're currently 2.5 million light-years apart. The collision is inevitable, written into the galaxy's mutual gravity. 4 billion years from now, give or take. The timescale is approximate. Collisions between galaxies aren't precisely scheduled events. But within that general time frame, Andromeda and the Milky Way will interpenetrate, the galaxies will pass through each other, their stars intermingling, their gas clouds colliding and triggering massive star formation. And eventually, after the galaxies merge, after they settle into a new configuration, their central black holes will spiral together. Sagittarius A star, 4 million solar masses. Andromeda's black hole, perhaps 100 million solar masses or more. The measurements are less precise than for our black hole, but it's substantially more massive. The merger will take time. The black holes don't collide immediately. They orbit each other, gradually spiraling inward as they lose energy to gravitational waves. Closer and closer over millions of years, eventually approaching the final plunge. The gravitational wave signal from that merger will ripple across the universe. Space-time itself will ring like a bell struck, carrying energy outward at light speed. Any civilizations with gravitational wave detectors will hear it. A distinctive chirp, rising in frequency and amplitude as the black holes spiral together, reaching a peak at merger, then ringing down as the new combined black hole settles. The new combined black hole will contain over 100 million solar masses, anchoring the merged galaxy. The resulting structure, sometimes called Milkomeda or Milkdromeda, depending on who's naming it, will be an elliptical galaxy probably. The organized spiral structure will be disrupted by the merger. What emerges will be different from either parent galaxy, and at its center will sit a black hole more massive than either Sagittarius A star or Andromeda's black hole alone. The combined mass compressed into a single event horizon, anchoring the new galaxy the way Sagittarius A star currently anchors the Milky Way. Life on Earth, if it still exists, will witness the night sky transform as the merger progresses over millions of years. Andromeda will grow larger in the sky, eventually dominating, eventually filling huge portions of the celestial sphere. The Milky Way's structure will change as gravitational interactions reshape it. Star formation will spike. The sky will be different, dramatically, beautifully, undeniably different. Whether humans will be around to see it? Unknown. 4 billion years is a very long time. The Sun will be nearing the end of its main sequence life. Earth's habitability may be compromised by the Sun's gradual brightening. Our species may have evolved into something else, or spread to other stars, or gone extinct, or transcended biology entirely. Who knows? But the merger will happen. And when it does, the monster in our backyard will meet Andromeda's monster, and together they'll create something larger, more massive, more gravitationally dominant, the new anchor for the new galaxy. Even darkness can be home, even when that darkness is scheduled to merge with another darkness billions of years from now. Sagittarius A star proves that supermassive black holes are common in galaxies, not rare anomalies, not unusual features. Common, expected, nearly universal among large galaxies. We've known this for a while now. Surveys of galactic centers consistently find supermassive black holes at their cores. But Sagittarius A star was among the first confirmed and remains the most thoroughly studied. Its existence, confirmed through decades of observations, through tracking stellar orbits, through measuring gravitational effects, established that supermassive black holes aren't exotic objects confined to distant quasars or peculiar galaxies. They're here, in our galaxy, at the center of everything we call home. And if our galaxy has one, probably most large galaxies do. Which observations confirm? Nearly every large galaxy harbors one at its core. It appears to be a rule. Not every single galaxy, certainly. Some small galaxies lack them, or have only intermediate mass black holes. But for galaxies of the Milky Way's size and larger, Supermassive black holes are standard equipment, like a feature that comes included rather than as an optional upgrade. Want a large spiral galaxy? It comes with spiral arms, a stellar disk, a halo of dark matter, and a supermassive black hole at the center. Package deal. The universe doesn't sell them separately. This has implications for how galaxies form and evolve. The black holes aren't afterthoughts, added later. They're integral to the process. They may even form before their host galaxies finish assembling, acting as gravitational seeds around which the galaxy grows. The relationship between black hole mass and galaxy properties suggests deep connections we're still working to fully understand. Studying ours helps us understand galactic evolution across the cosmos, because Sagittarius A star is close, because we can resolve individual stars orbiting it, because we can photograph its shadow and measure its properties precisely. It serves as a template, a reference case. The black hole we can study in detail to understand all the others we can only observe collectively. What we learn here applies everywhere. The physics at work in M87, 55 million light-years away, is the same physics at work in Sagittarius A star. The processes shaping the accretion disk around a quasar 10 billion light-years distant are similar to processes here, just at different scales or different feeding rates. Every measurement of S2's orbit tells us about gravity everywhere. Every EHT image of the shadow tests Einstein's predictions that apply across all of space-time. Every flare observed teaches us about magnetic field dynamics in all accretion disks, not just ours. Sagittarius A star is both local and universal, our own private mystery and a window into cosmic truths. A single black hole that happens to be unusually accessible, positioned perfectly for study, teaching us about the nature of all supermassive black holes through the simple fortune of proximity. It connects astronomy, physics, and philosophy in one mystery. Astronomy because it's an observational target, something we study with telescopes and instruments, something that requires careful measurement and patient data collection. Physics because understanding it requires general relativity, plasma dynamics, magnetic field theory, thermodynamics, all the fundamental physics operating at extremes. And philosophy because it touches on deep questions. What is time near a black hole? What does it mean for information to be lost beyond an event horizon? How do we know things we cannot see? What are the limits of the knowable? Sagittarius A star sits at the intersection of these disciplines, a physical object that raises questions beyond physics. It's a place where mathematics meets reality in particularly stark form, where Einstein's elegant equations predict the motion of actual stars moving at actual speeds through actual curved space-time, where theoretical predictions about shadows and time dilation become observable phenomena. And it raises philosophical questions about observation itself, about how we build knowledge of things we cannot see directly, about the relationship between theory and evidence, about what it means to know something exists when you can only infer its presence through its effects on other things. It reminds us that the Milky Way is a living, changing organism, not static, not frozen, not a fixed structure that's always been as we see it now. Galaxies evolve, stars form and die, gas flows through complex cycles, the black hole slowly grows, the whole system changes on timescales longer than human existence, but shorter than cosmic eternity. The Milky Way was different 1 billion years ago, slightly smaller, slightly less enriched with heavy elements. Sagittarius A star was slightly less massive, the stellar populations were different, and 1 billion years from now it will be different again, more massive black hole. Different stellar demographics, perhaps more or less star formation depending on gas availability. We observe a snapshot, a single moment in a 13 billion year story, but that snapshot teaches us about the broader processes operating across cosmic time, about how galaxies change, about how black holes grow, about how star formation evolves, about how the chemistry of the universe enriches from generation to generation. Sagittarius A star is part of that story, not just an object sitting at the center, but a participant in the galaxy's evolution, shaping star formation, recycling material, growing over time, influencing the environment around it, connected to everything else through gravity and magnetic fields and radiation. Looking at Sagittarius A star means looking at the Milky Way's history and future, means understanding how we got here, where the heavy elements in our bodies came from, how the galactic ecosystem has operated for billions of years. The black hole is a key to understanding home at the largest scales. It's also humbling. 4 million solar masses, 27,000 light-years away, 24 million kilometers across. These numbers are difficult to grasp emotionally, even when we understand them intellectually. The scale overwhelms human intuition. We're so small by comparison. Our entire planet wouldn't register as a rounding error in the black hole's mass. And yet we can study it, can measure it, can photograph its shadow, can test physics at its edge, can understand it, at least in outline through mathematics and observation. There's something remarkable about that, about the ability of small creatures on a small planet to comprehend objects so massive, so distant, so extreme. The monster in our backyard turned out to be comprehensible. Not completely, mysteries remain, but comprehensible enough, knowable enough, understandable enough that we can write equations describing its behavior, make predictions about its properties, test those predictions with observations. It connects us to the cosmos, reminds us we're part of something larger, that the Milky Way is our home, and at its heart sits this massive object holding everything together, that we exist in a galaxy shaped by a supermassive black hole, that our existence depends in part on its quietness, that understanding it helps us understand ourselves and our place in the universe. Even darkness can be home, especially when studying that darkness teaches us about everything else. The black hole ties together our galaxy's past and future, everything that has happened at the galactic center, everything that will happen, connects through Sagittarius A star. It was there when the Milky Way was young, probably forming in the early universe alongside the galaxy itself. It's been there through billions of years of galactic evolution, growing slowly, shaping its environment, anchoring everything. It'll be there in the future, continuing its role as gravitational anchor, growing as material falls in, eventually merging with Andromeda's black hole, continuing to exist long after stars have exhausted their fuel, after galaxies have merged and evolved, after time spans that dwarf even the current age of the universe. Black holes are among the longest-lived objects possible. They evaporate eventually through Hawking radiation, but the timescale is absurdly long. For a 4 million solar mass black hole, the evaporation time is measured in numbers that make billions of years look like nothing. Sagittarius A star will outlast stars, galaxies, perhaps everything else. Everything in the Milky Way, including us, exists in the architecture its gravity creates. We orbit the Sun. The Sun orbits the galactic center. That orbit is shaped by the combined gravity of dark matter, gas, billions of stars, and at the center, Sagittarius AY star. The black hole's 4 million solar masses contribute significantly to the gravitational structure that keeps the Sun in its galactic orbit. Without Sagittarius A star, the galaxy would be different, not dramatically different necessarily. 4 million solar masses is substantial, but not dominant compared to the galaxy's total mass, but different enough. The central stellar cluster would have different dynamics. The gravitational potential at the center would be shallower. The whole structure would be altered in subtle but meaningful ways. We exist within a galaxy shaped by a supermassive black hole. Our solar system orbits in a structure the black hole helped create. The heavy elements in our bodies were forged in stars that formed in an environment influenced by Sagittarius A star's presence. Everything connects, if you follow the chains of causation back far enough. To understand Sagittarius I star is to understand the heart of our home, not just intellectually, not just as abstract knowledge, but as understanding the place we live. The galaxy isn't just a collection of stars, it's a system, an ecosystem, a structure with organization and dynamics. And at the center sits Sagittarius I star, integral to that structure. Learning about the black hole means learning about home at the largest scales, about how the Milky Way formed, how it evolved, how it maintains its current structure, how it will change in the future. The black hole is a key piece of that story, not separate from it. Yet to peer into that heart is to glimpse the boundaries of human knowledge. We can measure the black hole's mass precisely. We can photograph its shadow. We can watch stars orbit it. We can test relativity in its gravitational field. But we cannot see inside the event horizon, cannot know what happens at the singularity, if the singularity even exists, cannot retrieve information that falls in. There's a boundary at the event horizon, not just a physical boundary, though it's that too, a boundary of knowledge, a limit beyond which observation cannot reach, where causality disconnects, where our ability to gather information ends absolutely. This isn't a limitation of technology. Better telescopes won't help. It's a fundamental limit built into the structure of space-time itself. 27,000 light-years away, there's a place we can never truly see, a region forever hidden from observation. The interior of Sagittarius I star remains unknowable, not because we haven't figured out how to look yet, but because looking is impossible. The universe has drawn a curtain and refuses to open it. And perhaps that's appropriate. Perhaps the universe is entitled to keep some secrets. We've learned so much, measured the mass, photographed the shadow, tested Einstein's predictions, watched stars dance at relativistic speeds. We've pushed observation to remarkable limits, but some limits cannot be pushed beyond. Mystery isn't always a gap in our understanding waiting to be filled. Sometimes mystery is the answer. Sometimes the boundary between known and unknowable is a feature of reality itself, not a temporary barrier but a permanent structure. And there's strange beauty in that, in knowing we've reached a limit, in accepting that some questions have no accessible answers. Sagittarius I star teaches us about boundaries, about what we can know and what we cannot, about the difference between temporary ignorance that future discoveries will resolve, and fundamental unknowability that no amount of clever observation can overcome. The event horizon marks that difference. On one side, the knowable universe. On the other, whatever happens there, forever hidden. In the silence at the center of everything, 4 million suns worth of mass curves space-time back on itself. Nothing dramatic about it, nothing violent, at least not currently. Just presence, just gravity, just mass existing in space, bending the fabric of reality, creating the architecture that holds 400 billion stars in their orbits. Creation and destruction constantly balanced. Stars form in molecular clouds, shaped by the black hole's gravity. Stars die and their remnants drift inward. Matter falls in, disappearing beyond the event horizon. Energy radiates outward, ionizing gas, affecting the next generation of star formation. The cycle continues, has continued for billions of years, will continue for billions more. And we exist within this system, orbiting the Sun, which orbits the galactic center, which orbits Sagittarius A star. Everything connected through gravity, everything shaped by the silence at the center. The monster in our backyard isn't monstrous, it's the anchor, the heart, the quiet power that holds home together. In that silence, in that still center, there is beauty beyond words. Not the beauty of visible light or dramatic events, the beauty of structure, of gravity patiently holding everything in place, of time scales so long that human existence barely registers, of processes operating for billions of years, creating the conditions that allowed us to exist and wonder about them. Sagittarius A star doesn't announce itself, doesn't demand attention, doesn't produce spectacular displays. At least not usually. It just sits there, 27,000 light-years away, invisible to our eyes, detectable only through patient observation and clever instruments. Silent, dark, present. The silence at the center holds everything together, not through force, not through violence, through gravity alone, operating across vast distances, shaping orbits, creating stability, providing the gravitational foundation for galactic structure. 4 million solar masses compressed into darkness, yet that darkness is essential. That darkness is home's foundation. We circle it distantly through the Sun's slow orbit around the galactic center, one circuit every 230 million years. In our lifetimes, we barely move along that orbit. In our species' existence, we've completed a tiny fraction of one lap. But we're moving, following the path that billions of years of gravity have carved through space. And at the center of that path sits Sagittarius A star. Patient, persistent, permanent, at least on timescales that matter to us. The monster that turned out not to be monstrous. The darkness that turned out to be home's anchor. The silence that speaks through the motion of stars and the curvature of space-time. Where gravity bends light and time. Where the gentlest force creates the deepest well. Where 4 million solar masses wait in stillness, holding everything together while remaining invisible. Where mystery meets knowledge at a boundary we cannot cross. We live in a galaxy with a supermassive black hole. Our home depends on something we'll never fully know. The boundary between known and unknowable is marked by the event horizon, a mathematical surface separating what we can observe from what we cannot. Some questions have no answers, and that's not failure. That's the way reality is structured. Even darkness can be home, especially when that darkness holds everything together. Especially when that silence creates the space for stars to form, planets to orbit, life to emerge, consciousness to arise and wonder about the center of everything. The monster in our backyard. The silence at the heart of home, Sagittarius A star, where darkness becomes foundation and mystery becomes belonging. And so we return to silence, not absence but presence. 4 million solar masses compressed into stillness, the anchor at the center of everything we know. We began with invisible radio whispers in 1951. Karl Jansky's antenna catching signals from the galactic center, not understanding what was speaking. Decades of observation followed. Bruce Balick and Robert Brown confirming the compact source in 1974. S2 and the other stellar dancers revealing the black hole's mass through their orbits. 20 years of watching stars trace ellipses around darkness. From mathematical prediction to measured reality. Einstein's equations, published in 1915, predicted black holes as theoretical possibilities. For decades they remained mathematical curiosities, solutions to equations that might not exist in nature. Then we found them, not in some distant galaxy, but here, at the center of home. We track stars for decades to prove it exists. Patient astronomy, night after night, year after year, watching stars move across images, measuring their positions, calculating their orbits, building certainty through accumulated observations. S2 completing its 16-year circuit, S4714 racing, passed at 8% of light speed. Dozens of S-stars mapping the gravitational field through their motion. Einstein vindicated across all those decades, relativity tested to 0.3% accuracy, gravitational redshift measured, orbital precession observed, time dilation detected, every prediction confirmed. Century-old mathematics describing reality with remarkable precision. We built a planet-sized telescope to photograph the shadow. 8 radio dishes from Hawaii to Antarctica, working together as one enormous virtual instrument. Petabytes of data, years of processing, algorithms dealing with a target that wouldn't hold still. And on May 12th, 2022, the image appeared. An orange ring glowing against darkness, the shadow of Sagittarius A star, our black hole, the heart of home, photographed at last. We measured the unmeasurable at our galaxy's heart. Mass, 4.3 million solar masses. Distance, 27,000 light-years. Size, 24 million kilometers across. Properties that seemed impossible to determine, yet determined through careful observation and clever physics. We confirm that home has a black hole at its center. Not speculation, not theory, confirmed fact. The Milky Way's structure depends on it. Our sun orbits around it, distantly. We exist in a galaxy anchored by something we can never fully see. What remains unknown? The singularity, forever hidden behind the event horizon. The interior structure, unknowable by the laws of physics. Why Sagittarius A star is so quiet compared to other galactic centers. How exactly it will evolve over deep time. The details of what triggers its occasional flares. Mystery as feature, not flaw. The event horizon marks a genuine boundary, not a temporary limit of technology, but a permanent structure of reality. Some things remain unknowable, and that's profound rather than frustrating. The universe is entitled to its secrets. 27,000 light-years separates us from the center, close enough to study in unprecedented detail, close enough to resolve individual stars orbiting, close enough to photograph the shadow, far enough to be safe from tidal forces, far enough that the radiation environment doesn't threaten us. The perfect distance for wonder, for observation, for understanding without danger. Look up tonight, knowing Sagittarius A star sits at the center of the band of light stretching across the sky. You can't see it, of course. Dust blocks the view. The black hole itself emits no visible light. But it's there, in that direction, at that distance, silent, dark, invisible to our eyes, yet photographed, measured, understood in outline, if not in every detail. After 50 years of knowing it existed, after decades of patient observation, after years of building instruments capable of seeing the unseeable, we finally saw its shadow, confirmed its presence visually, made the invisible at least partially visible. The monster in our backyard. Except it's not monstrous at all. It's the anchor, the foundation, the gravitational center around which everything orbits. Quiet, understated, doing its work through gravity alone, without announcing itself, without demanding attention. The silence that holds everything together, not through force, not through violence, Through patient gravity operating across billions of years, 4 million solar masses, creating the gravitational architecture that makes the Milky Way possible. That keeps stars in their orbits. That shapes the environment where we exist. Where gravity bends light and time, where space-time curves so severely that escape becomes impossible, where physics operates at extremes we can barely imagine, where Einstein's predictions become observable reality, where the gentlest force creates the deepest well. Gravity is the weakest of the fundamental forces, yet given enough mass and enough time, it creates black holes, compresses matter until space-time breaks, creates regions where the normal rules of physics give way to something stranger. We live in a galaxy with a supermassive black hole. This isn't unusual. Most large galaxies have them. But it's our black hole, our galactic center, the heart of the structure we call home. And its quietness, its restraint in feeding, has shaped our existence in ways we're only beginning to appreciate. Our home depends on something we'll never fully know. The interior of Sagittarius A star remains forever inaccessible. We can measure its mass, photograph its shadow, watch stars orbit it, but we cannot see inside, cannot know what happens at the center, cannot retrieve information that crosses the event horizon. And that's okay. Some mysteries don't need solving, some boundaries don't need crossing. The limit at the event horizon is permanent, built into the structure of reality itself. Learning to live with that, to appreciate it rather than lament it, is part of understanding our place in the universe. Some questions have no answers, and that's profound. Not every mystery is a puzzle waiting to be solved. Sometimes mystery is the answer, the acknowledgement that reality has limits, that knowledge has boundaries, that some things remain forever beyond reach. Sweet dreams under stars that orbit the invisible, 400 billion suns, each following its path through the galaxy, each orbiting, ultimately, around Sagittarius A star. The structure is beautiful, the dynamics elegant, the timescales beyond human comprehension, but it's real, and it's home, and we're part of it. Rest knowing the center holds. Despite the vast distances, despite the dark matter we can't see, despite the complexity of the galaxy's structure, everything holds together. Sagittarius A star anchors the center. Gravity shapes the orbits. The system is stable, has been stable for billions of years, will remain stable for billions more. The darkness at the heart of everything, not threatening darkness, not fearsome emptiness, darkness that creates structure, darkness that enables existence, darkness that holds the galaxy together and makes our existence possible. The kind of darkness that reminds us even darkness can be home. Sagittarius A star, where silence shapes reality, where 4 million solar masses wait in patience, where the boundary between known and unknowable becomes visible as a shadow against glowing gas, where home's heart beats in gravitational rhythms we can measure but never fully comprehend. The galactic heart, forever hidden yet forever present, invisible to our eyes but visible to our understanding, unknowable in detail but comprehensible in outline, the monster that turned out to be an anchor, the darkness that turned out to be foundation. This is the Sleepy Astronomer, wishing you sweet dreams under stars that circle the invisible. Rest well knowing that silence holds everything together, including you. The universe is stranger than you imagined, more wonderful than it appears, and more mysterious than it will probably ever reveal. And that's exactly as it should be.